The next talk is by Andun Lee on the theory of hard diffraction and asymptotics and the predictions for. Start sharing your slides.
Okay. Can you hear me, Jim? Well, thank you for giving me this opportunity to talk in this conference. And today I will talk about our recent work on diffraction for future electron-ion collider. And our study is motivated by the observation of diffractive events in the ethera, in the electron-proton collision. And in particular, the diffractive event were accounted for about 10% of total event at HERA. And indeed, this observation boosted the saturation physics. And what we have for the electron-proton collision is also expected to see in the future electron-ion collision, which is also a key motivation for our study of diffraction. And our study is in framework of the deep inelastic scattering at high energy, which can be described using the dipole picture. In this picture, the virtual photon will split into a quark anti-quark pair long before the interaction with the nucleus. So we can write the total cross section of the photon as the convolution of the wave function of the photon and the dipole cross section. So the understanding of the virtual photon diffraction can be translated into the understanding of the diffraction of the dipole. So
sorry, could you please put a full screen, maybe, if you can? Or...
So my talk will include two parts. First, I will talk about the theory of diffraction in the dipole nuclear scattering. And then I will present a phenomenological study of diffraction in the virtual photon nuclear scattering. And what we are interested in is the distribution of the rapidity graph. Now I will start my talk, my first part for the diffraction of the small dipole. And first, I will make a very short review on the high energy evolution of the dipole in the color dipole picture. And when we increase the rapidity, one short balloon can be emitted in the wave function of the dipole, and in the large number of color limit, this balloon emission can be treated at a dipole branching with the probability given by this kernel. And when we boost the dipole to a higher energy, this dipole branching will be repeated independently, and to the end, the first state of the dipole evolved to high energy is essentially a set of dipole with various size characterized by some random density. And the scattering of the dipole with the nucleus can be described using the evolution equation. In particular, the asymmetric element of the forward elastic scattering can show the Balinsky-Kopchagov equation, which the inertial condition determined at zero rapidity by the Goleb-Bernoulli or the Maclaurin-Van model. Meanwhile, the diffraction with a minimal rapidity gap y0 is encoded by some function SD, defined as the rapidity y0 as the square of the elastic asymmetric element, and it also obeys the BK equation. So to get the gap distribution, we just need to take the derivative with respect to the y0 of this function. And so the equation forms the Kopchagov-Levin formalism for the diffraction. But they are really challenging to show it in an exact way. So the scattering and the diffraction of the dipole with the nucleus can also be described using the by looking at the detail of the evolution in the frame where the nucleus is boosted to some rapidity y0, and the dipole evolved to remaining rapidity. And by the optical theorem, we can write the total cross section at 2 times the forward elastic scattering amplitude. And for the diffraction, since this process is elastic at the level of the nucleus, we can write the diffraction procession like this one, and we also take the average over on the possible configuration of the Fock state of the dipole equal to the rapidity y minus y0. And in the two formula for the for two cross sections, the S function here is the S function of the is the S metric element for the set of dipole with various size interacting with the nucleus. And since each dipole in the first state interact with the nucleus independently, we can you can write this composite S metric element as the product of the on the S metric element for each dipole. And after some manipulation, we can write this composite S metric as the an exponential. And now we are interested in the scattering of a small dipole with the nucleus. And the small here means that the size of the dipole is much smaller than the inverse software scale. And in this case, the relevant configuration giving the dominant contribution will contain small dipoles such that the corresponding asymmetric elements is close to 1. So we can use a simple approximation, and to the end, the composite asymmetric here can be expressed as the exponential of the overlap between the dipole density and the scattering amplitude of the dipole nuclear scattering. And from the expression, the above expression for the total cross section, we can write it in terms of we can write this the total cross section in terms of the probability of having at least one dipole in the first state effectively scattering with the nucleus. And also we can write and also the diffractive cross section proportional to the probability of having an even number of participating dipoles. So to calculate the two cross sections, the remaining thing to do is to take average over on the dipole configurations. And to do that, we look into the detail of the evolution of the initial dipole. And as we know, the first state of the dipole at each rapidity is a random set of dipole with various size. And if we take the mean field approximation, the evolution will be deterministic in a way that the typical realization of the first state of the dipole will contain dipoles with the maximum size determined by this scale. And also we can find the mean field density of the dipole by solving the BFK evolution equation. Now, if we let this typical first state scatter with the nucleus, since the initial dipole is very small, much smaller than the inverse saturation scale of the nucleus, the overlap between this typical state with the nuclear scattering amplitude will be insignificant. So what we need is a fluctuation at some point in the evolution of the dipole of the initial dipole, and this fluctuation will create a large dipole far from its mean value. And this dipole then will develop into another mean field tree, and then overlap with the nucleus to give the dominant contribution. So the average over on the dipole configuration is equivalent to that integration over on the rapidity of the fluctuation and over on the size of the fluctuation weighted by probability density of the fluctuation. So our model is indeed a combination of the mean field evolution and a single fluctuation during the evolution. And using this picture, we can derive the expression for the weight W, and if we take the ratio between the probability of having many participating dipole to the probability of having exactly two participating dipole, then the ratio or the obtained ratio will decay slowly. So events involve many participating dipole are not rare at all. And with the expression of the weight W, we can deduce the expression for the diffractive construction for minimum gap y0, and also for the rapidity gap distribution. And actually, the functional form of the distribution in known before, but not just over the constant. And in our approach, this constant is completely determined. Now I will move at the diffraction in the electron ion collision. And in this study, we did a numerical calculation based on the dipole factorization of the deep elastic scattering, and based on the Kopchagov-Levin formalism, including two PK equations for function for the S matrix and for the function SD. And also we consider both the fixed coupling and the running coupling kernels for the BK equation. For the kinematic, we pick a value of rapidity and the photon volatility in accessible at the BNL EIC and LHC. And in the first place, we plot the diffractive scattering with a minimal graph. First, we plot for the case of fixed coupling, and we see that the diffractive event accounted for a significant ratio. For example, about 20 to 30% at the rapidity y to 6. Then we will plot for the case of the running coupling, and we see that we see a bit higher ratio for the running coupling case. Next, we plot the gap distribution, and we see that the shape for the distribution for the fixed coupling and for the running coupling case are different. And if we look at the shape for the fixed coupling, they have the quite similar shape to the prediction of the gap distribution for the case of in the dipole nuclear scattering. It become more clearly when we look at the higher rapidity. So representation for scattering, we see the and the multiple exchange are typical for diffraction. Well, we also did a numerical study of the diffractive scattering in the electron ion collision, and made some prediction for the gap distribution and also the diffractive to the total scattering ratio. In this study, we consider different scenario, and there are many things for the perspective. For example, we can extend the study for the case of running coupling, and for the determination of the subasymptotic correction. So that's all for my talk. Thank you.
Yeah, thank you very much for this nice talk. Are there any questions or any comments from the audience? Please go ahead. Now is your time.
Yeah, maybe I have a question. Sorry that I cannot raise my hand as as co-host. So yeah, I have a question to know if the would it be possible to use as an observable ratios with different heavy ions at the EIC that might make disappear some uncertainties related to the predictions on scale, or also some experimental uncertainties. So I was wondering, is measuring ratios of distribution between different heavy ions would be something good to study?
Yeah, I'm not sure about the experimental, but you mean this ratio?
Yeah, but you do the measurement, I mean, for different heavy ions, and then you take the ratio between the different curves. Let's say, for instance, I mean, I don't know, gold, lead, or because the advantage of the EIC is that we will be running for many different heavy ions. That it could be for light ions or also for heavier ions. So I was wondering if doing this measurement and then taking the ratio for different heavy ions would be a good test of your formula and your study. I mean, I don't know.
Yeah, I'm not sure, but yeah, it would be interesting to consider be different nucleus, but what we based on is the BK formalism, and strictly the BK evolution I mean it good for heavy ion, not for the light ion.
Yes, for heavier ions, but still maybe taking a ratio between two different heavy ions will make some uncertainties on the formula, or I mean, disappear or something like that. Again, I don't know, and simplify the prediction.
Yeah, I'm not sure. Yes. Yeah.
Mm-hmm.
Okay, are there any more questions? Any more comments? Somebody else in the audience? Okay, then I think doesn't seem to be the case right now. So again, thank you very much for this very nice talk, and maybe we can come back to this later on in the discussion session. But I think for the moment, I think it's better we go on. So again, thanks a lot for this talk. Okay. And the next presentation, it would be now by Javier Alberto, as far as I can see, on particle correlations in small systems. So yeah, we're sharing great. So again, please go ahead whenever you're ready.
Can you hear me?
Yes, very well, thanks.
Okay, so so this is so I prepared this talk with not a very long time of anticipation, but here I summarize some of the recent efforts on the study of particle correlations in what are called small systems, and where there exists a lot of models for example, these effective color glass condensate models that are associated with the prediction of the ridge formation, for example, in proton-proton collisions. So I will give an introduction, and then there are recent explorations with small systems with the experiments. Well, some archived data from CEUS, Alep, and some others, and some recent measurement or search by Atlas in the LHC. And then there are some current studies and ideas that we could attempt with CMS. So in the slide 3, so this is the introduction. So there are these long range of correlation that you can have along this axis of pseudo rapidity. So you take the two particle difference of pseudo rapidity, and then you have to, so I will talk a little bit about the process that you have to follow to build this plot. But the aim here is to observe these sort of structures that go long range or that go to high values, up to high values of this axis of delta pseudo rapidity. And this structure, particularly the one that you see in near side in delta phi equals 0, is quite common. For example, you see here gold-gold collisions and lead-lead collisions. And you can see this structure that is known as a ridge. But if you attempt something like deuterium gold, then you get to see it's not clear. You can measure some properties, you can characterize the structure, but it's not clear whether or in which system you will see this same effect. So at that time, sorry, yep. Okay, there was some noise there. Okay, so it was not clear, for example, in the scope of this publication, whether you will see this in smaller systems. But if you go to and well, before going to the proton-proton observation, here you may have systems, small systems, such as the one I mentioned, a deuterium gold, in where you don't have a clear formation of this correlation in the delta phi 0 line here, for two different categories here of PT, 3 to 4, 4 to 6. But you have the formation of the structure with a larger system, for example, gold. You can measure the area of this structure. There is a procedure in where you calculate the minimum in certain range around this region, and then you calculate the significance of the area of this structure. And this is something that can be done easily with large systems such as lead-lead or gold-gold. And you can even set upper and lower limits of this of the significance of the area that you have for the ridge. And then recently, there have been attempts to set limits on these areas for smaller systems, in where there's no clear idea of what happens in terms of the correlation itself. There are two approaches. So one is based on the origin of the ridge might not be the formation of let's say color glass condensate, but it could be arising from fluctuations associated with the initial gluons, for example. That could be the gluon distributions within the protons. But the idea is behind a fluctuation effect. And then there is another idea that could be on the actual formation of a state that exhibits properties such as the quark gluon plasma, and can be explained in the context of hydrodynamical models, and it can be connected with some properties that can be measured, such as anisotropies or Fourier coefficients that are associated with the transport properties of the expansion of this medium when it's formed. And here I'm showing the proton-proton one. So in this case, you can see proton-proton here, high multiplicity. In this case, what is seen is that the formation of this correlation is the long-range correlation is stronger, not for the highest PT, not for the lowest one, but for an intermediate PT category. And the same behavior is seen for proton lead, where this correlation is the formation of the ridge with significant area here is seen. So there are, so I'm not putting a lot of details on the theory, but there are models that predict the formation of the rich structure in proton-proton, for example, based on these effective models of color glass condensate, and this is related with the gluon saturation, for example. But I will focus more on the diffraction side, which is for example, the search that we attempted on, for example, photon-proton collisions, in where you have this formation of rapidity gaps. But there is discussion and relation with the saturation effects that are connected with the reach. And here, this is a summary here in slide 6, in where, for example, for the case of proton-proton, you have to be at the high PT, have to isolate high multiplicity events, sorry. For example, here we have events that have at least 110 tracks, but here you don't see, even when you have high multiplicity, you don't see the formation of the structure. But here you see it when you adjust the PT to be in an intermediate category, as I mentioned it before. It's not clear, the image here. A summary is here below, so you can see that you keep increasing the PT, and not necessarily for highest PT you see the highest significance of the reach, but it happens in this intermediate region that is between 1 and 3. So this is the required PT for the tracks that participate in the correlation. So you ask them to be between 1 and 3, or you can split them in two bins, 1 to 2 and 2 to 3. Here you don't see the structure, even where that PT is quite large, is the largest. These are the largest values for this analysis, and you don't see the a significance for the reach. There are some other studies that have been focused on trying to see differences between the proton-proton, proton-lead, lead-lead systems. There is another technique also that I'm not putting a lot of information here, but it's based on the Cumulan technique, where you can calculate correlations not only from that two-dimensional structure that I showed, but you can measure these coefficients that actually characterize the system that is let's say if you have the formation of a certain state that is consistent with the hydrodynamical model, you can characterize this with this coefficient, for example, that is known as an elliptical anisotropy. And you can calculate this using two particle correlations. So you can compare pairs of particles, or you can compare groups of 4 particles, 6 particles, 8 particles. So according to the recent studies, it is expected that if you have multi-particle correlations, there is a consistency in the value of the B2, as you can see here, for 4, 6, and 8 particle correlations. But you can see 2 particle correlation here that is larger, has a larger B2 than with respect to the other ones. And there are also ideas on that that have to be with additional fluctuations that come or are related with the 2 particle case. But what is calling more the attention here is that the magnitude of the values are larger for the lead-lead case, and it has to be with when this collision occurs, that there is the highest possibility of having an overlapping area here for the lead-lead system, and that reflects in a larger value for the what is called the ellipticity, or which is basically this B2 value. There are other properties that are associated with another coefficient, which is this B3. So I will talk about them in the following slides. So here we go into a smaller system, let's say electron from Alep archive data. So this is a paper that was, so it's a 2019 paper, a very recent. And there is an effort of searching for this correlation in any system. In this case, this is much smaller than lead-lead or even proton-proton. And here, here you don't see in this study the evidence of the correlation, of a long-range correlation. You see a lot of jet-like effects. So you have the formation of this peak here, because if you have a jet, you have a lot of charged particles that are very close in angular variables in these two, pseudo-rapidity and azimuthal angle, and then you will have the formation of this peak. But if you have a dijet structure, then you have that they will peak at the pi, which is if you have this dijet formation, it is very possibly that they will be with this back-to-back topology, and then you will have a lot of contributions on this side. But in the near side, which is where there is connection with this, the formation of these states and the ridge and so on, there is nothing. So then the other thing that calls the attention is that the actual range or the limit of these systems is very limited. So you can see that here you are about 35, and basically you have all your data. And this measurement is based on isolated events that go higher than 35 in track multiplicity. But you can see that the fraction of the data is 0.5. And the average of that data is basically stuck to the lower limit, which is 35. So in here, you can see this is the sort of fits that you do. And then you can see that if you had the formation of the ridge, so to build this area here, you have to project this into the highest delta eta. So you can explore this region that is in red circles here. And if you had the ridge, you will have the formation of some sort of a structure here around 0. But here you can see that if you calculate if you try to calculate an area with respect to the minimum here, you wouldn't get anything from these results from Alep. So you can generate templates with different values of B2, for example, which is what they did. In here, the analysis is more complicated because you can adapt your analysis to two reference systems. So you can take the dijet axis, that is the truss axis, and you can generate another version of eta and azimuthal angle. But in neither of them, you can see with the data any significance here. You can see this. Okay, this is the same study. So what they did is they compared with the different Monte Carlo models, in where it seems that in here the conclusion, I think, was that Pythia and Sherpa were better consistent with the data, and Herwig was the one that differed more. And they set upper limits. So you can see that there's no area, there's no reach, but you can see upper limits. For example, if you see proton, or if you see proton, or you see proton lead, you can see that at some point the area has a lower limit in here, which are these green and sort of blue markers here. You can see that there is an upper and lower limit, but for the case of electron, there is only an upper limit that is very low for in this region of track multiplicity, but it gets a larger value because the uncertainty gets really large in the last part of the range of track multiplicity. Okay, so you can see as well the case of electron-proton, so not electron-electron anymore. So this is similar to the analysis of photon-proton in terms of the, for example, we have very similar track multiplicity than with respect this analysis from CUs. And you can see that there are comparisons at generator level and reconstructed level from some Monte Carlo models. In this case as well, there is no clear observation. In this case, as well, you see for this small system a very limited track multiplicity, as in the case of electron-electron. So the actual range of the system is very limited. So the aim here was to try to search for the reach, for example, in the last part of the range, as in the same way as you do with the proton-proton, but there's no significance there. With respect to how these coefficients and the anisotropies behave, this is very similar to what we saw with CMS in photon-proton. So if you don't ask for anything, you can have these V1 and V2 coefficients, which could be positive. But if you require PT cut, for example, then you see that the value, for example, the V1 starts getting negative, and the V2 gets positive. That happens, as I have seen, usually when you don't have a long range correlation. And if you increase the PT requirement, you can see that the magnitude of the V1 gets larger, and the magnitude of the V2 gets larger as well. But you can see that the V1 magnitude is larger than the V2. So that also has to be with expecting no reach. Here as well, you can see another behavior in terms of the PT, and for two different track multiplicity categories. So it is understood that if you have the highest track multiplicity and the highest PT, you will get a larger value of this for the value of these coefficients. So this is very similar to what is in CMS with the photon-proton. There is another study which is similar to the previous one, the CUS one, which is the electron-proton. And here you can see that as well is a similar situation with very limited N-track. You get to see this sort of distribution where you are trying to explore the last part of the tail of your range. You see this dijet structure here, and you don't see clear formation of correlation in this axis around 0. But what's sometimes a problem is that at the edge you get to see these fluctuations here. that sometimes can sort of imitate the ridge. So one has to be careful here, because sometimes these fluctuations, when you project this 2D plot, can sort of imitate the shape of the ridge. For this case, they set limits on the area of the ridge, which is consistent with 0. You have larger interact, you have larger uncertainty, but there is consistency with 0 as well. With here, I mean, from H1, that is very similar to CO's result. So the two here results are consistent with each other. And then you have this Atlas result that is exploring the photon LED case within LED collisions. So this system is a bit larger. So you get a limit on the track multiplicity that goes up to 80 in this case. But if you explore, so there is a range in track multiplicity here. So if you go really high, you possibly won't have statistics within this plot. It depends on the PT requirements that you do here, or the track multiplicities that you use. But here, for example, they use 30 to 37, which is somewhere around here. And then you see that the plot is fluctuating a lot. So it's not smooth. But there is no indication of a correlation around 0, long range correlation. But in here, what they do is they measure actually significant values for this elliptical anisotropy. So that means it's not 0, which contributes to these studies, because you don't have evidence of the ridge, but you have significant ellipticity, which is one of the properties that are associated with the hydrodynamical models that are in the site of a formation of a state that is sort of expanding. So at least in this case, we have significant values that are smaller than the proton-proton or the proton-LED cases that you have here, that can expand up to much larger track multiplicity. You can see that the gamma LED ones are stuck to really small N-track. So these are the averages of the corresponding bins that were used. This is the same distribution of the track multiplicity that goes up to 80. And is compared with different Monte Carlos, which I think the one that matches better, at least at the highest end track, is this ZPM jet gamma LED. And this is compared with two models of gamma proton. I think this maybe used the most recent PTI photon flux from the LED, but I'm not sure in this case if it's a proton LED collision or LED. But that's okay. I think this should be LED proton. And then for the case of CMS, so we explore. We can use different detectors to generate or identify rapidity gaps. So we can use these 0-degree calorimeters that are 100 meters from the interaction point. We can use the forward calorimeters to set constraints on particles and activity on each of the sites, depending on which particle you want to be intact, so not having a break-in effect. So this is what you can use. And for example, for the photon-proton, these are ultra-peripheral collisions. So there is a paper that is under update right now. So I'm not showing the current version of the plots, But so what we do is we compare photon proton with minimum bias. Minimum bias is what was observed first with proton lead collisions, and it was observed that there is no doubt that the ridge effect exists. So we use that as reference. So this is within the proton lead collisions at the LHC at 8.16 TeV. And these are the individual energies of the proton and the lead at the LHC. So this is the type of topology that you see. So you have, so in this case, the lead that provides the photon goes intact in this side, and then the proton goes in this direction, and all the activity goes in this side of the detector. So you have certain requirements that can isolate these kind of events. One of them is the formation of this rapidity gap, and to have constraints on the activity on this side, and also to require activity on this side where the proton is going. Okay, so for this, there is this impressive consistency with this recent PTI-8 model that I'm referencing here. So this is the data that we claim is at least 95%. It has a purity of at least 95% of photon-proton, and these are generated events of photon-proton with this new PTI-8 model. And you can see that the limit is pretty much very similar, and also the shape of the distribution. We put them over each other, but that's the updated plot that I mentioned at this the progress. But you can compare with the minimum bias range that can go up to over 250 at least. So this can go much larger. But you can see here, this is similar to what Zeus and H1 were seeing on electron proton that is limited up to 30. So I think there won't be time to explain the actual technique that we use, but pretty much you have an event and you can compare tracks, individual tracks of that same event with these angular variables that I mentioned before, and you build a preliminary correlation distribution. But also you can compare each track with random events that have similar features, and then you generate this background distribution. So when you have this mixed events distribution and these same event pairs, you can take the ratio of these distributions, and that's what builds the two correlation plot that I showed at the beginning of the presentation. And that's the structure that we use to search for the ridge and the long range correlations, which is this distribution here. That so we know that for proton lead you see the ridge, but not when you reduce the track multiplicity to really low values. So you don't see ridge here. And with photon proton, you're using all the statistics here, and you don't see evidence of the ridge as well. So this is the projection as well. You don't see evidence. You don't see any information here. At this same range of track multiplicity, the gamma proton and the minimum bias results are very similar. These are the coefficients that are actually can be calculated with this Fourier fit. This is another approach that you can use. You can perform this fit from 0 to pi. Here the result, from this fit, you can separate in different components. For example, this one is associated with the V2 value. You have this one that is associated with the V1. So this is why I was saying that if V1 is much larger than the V2, then that won't help with the formation here of the ridge, because obviously this green component will dominate in this region. So these are have been updated, but will be released soon. But here you can see the data, and here you can see the Monte Carlo, and there's actually consistency in the behavior of the Monte Carlo with no ridge effects and the data. So you can see, for example, that it reacts to the PT increase. So you increase the PT, and then you see the larger magnitude of the B1, of the B1 and the B2 values. We see a B3 that is consistent with 0, and as well the Monte Carlo is giving that sort of behavior as well, which is another indication of no long-range correlation. But you can see that the Monte Carlo exhibits an increase in the coefficients values, the B2 values and the B1 values, and also the behavior is very similar. Okay, this is another, with those coefficients, with the B2, you can calculate this anisotropy. And you can see that even when the Monte Carlo, this is the Monte Carlo again, and above is the data. So the Monte Carlo of gamma proton is consistent with the gamma proton events, but both of them are larger than the minimum bias results. So this is something I think to understand why you see this larger value. It could be due to additional correlations associated with jets, for example. I don't know. We are so to close. There is a possibility. There is one student that is working on this exploration of attempting, for example, since Atlas attempted photon LED, we could attempt, for example, Pomeron LED, which is a bit larger system because we see a larger N-track distribution. We will be showing that soon when we have a more consolidated analysis. But this is a sort of diagram that is representing that you have the proton intact and the LED that breaks. And there is a study from CMS that is this past physics analysis summary that is public in the CERN website. And you can see that there is separation, or at least there are estimations with Monte Carlo of non-diffractive contributions. And then you can see use this selection to study these correlations in this system of Pomeron LED interactions. There is a selection that requires or constrains that the proton remains intact and the activity goes in the LED side. Okay, this is so there are other possibilities. Since there are at least, for example, new updates in Pythia, for example, you can explore the case of, for example, with this electron photon approximation, you have this photon flux, but you can also go a bit smaller than the system I just showed before. You can attempt a photon Pomeron, for example, which is something that will be interesting, because in this case you will request the LED and the proton to be intact at the end of the event. I mean, you will require them to be intact, and then you will have the formation of charged particles here, which you will use to do this study. So this is something that could be left to for a future search. But we are actually generating some events from this sample, and we're trying to see what's the kind of N-track range that you will get. But there was no. I was initially planning to show this for this talk, but there was no time. So to close the talk, so for these recent searches, studies of these anisotropies and Fourier coefficients, and also there is this technique on the cumulant, there are some similarities on these smaller systems, for example, electron-electron, electron-proton, and gamma-proton, in where you get to see a negative value of V1, V2 to be positive, and a V3 that is consistent with 0. You have very limited N-track range that goes actually for these three systems to something up to around 30 or 35. And you don't see evidence of a Ritz-like correlation. And I'm missing here the result from Atlas that goes higher in an N-track multiplicity. There is no Ritz, but they see also what is called significant values of these coefficients. So there are current explorations, for example, Pomeron LED, or there could be another exploration with the Pomeron photon, for example, which will exhibit the photon and the LED to be intact. This could be searched as well in proton-proton collisions. So these results contribute to the studies or insights for Ritz-like structures in small systems. So that's all.
Thank you very much, Javier, for this very nice talk. Are there questions, comments from the audience? Please go ahead. Raise your hand or just talk. It's fine. Oleg, please.
The parity implies that V1 is an odd function of rapidity. And for large systems, the appearance of even function is associated with some fluctuation in coordinate space. Is it possible to look for such even function of V1 for small systems? Maybe they can somehow be related to Oderon. Is it possible to say something?
You mean the dependence with respect to rapidity, or
exactly?
The other...
So the parity implies that V1 is odd function of rapidity and crosses 0 for rapidity 0. And for large systems, it's some even component, and it's associated with some fluctuations. And my question is about small systems. Maybe it's some ways to Oderon for some just different parity contributions.
Yes, I think that behavior that is in larger systems can be explored. Yeah, I don't have a clear answer to that, but that dependence with the rapidity can be explored. Actually, I didn't show the dependence with rapidity. I maybe should have, because here, as you can build these distributions with respect to the PT, you can build them with respect to the rapidity. And yes, that's something that actually was done by Zeus on this electron-proton result, but I just don't have the actual plot here. But you're right. There is a dependence with the pseudo rapidity. It's just that I didn't include that here. I think so. I think yes, this could be attempted with other systems.
Okay, thanks.
Okay, thank you very much. I think we should now go on to the next talk because we went a bit over time. Maybe no questions. We can go to the. Christoph, you want to say?
Maybe I just would like to come back maybe to the the link between the ridge and the color glass condensate model, because since, as you said, I mean, we see it both in PP, PA, and AA, but we don't expect to have a saturation region when you use PP, I mean, at the LHC. So I was wondering if it doesn't show that it's something else that is not related to saturation and not color glass condensate models, because I don't know, it's at the edge to be able to apply this model for PP maybe, because we are probably, I mean, in the value of X that we have at the LHC, for this measurement, we may be far away from saturation region, no? Or it may be more collective phenomena that appears rather than saturation effects. Or what do you think? I mean, yeah.
Yeah, there are some distributions as a function of the scale in this paper here that I'm referencing. There are many papers. This one was released when this discovery occurred, and there is a discussion on the different effective models. Well, there is one effective model on color glass condensate, and it talks about the gluon saturation and the causality of what may be happening in terms of time. So about that specific, to answer that, I possibly in other time can focus on the model itself, like the one that is described here. I just can say that at least under that framework that is described there, there is expectation of formation of a ridge in proton-proton. But that's under that model. I'm not giving details of that model here, but at least under those terms that are described there, there is expectation for the formation. But yet, just to talk about the gluon saturation.
Yeah. And do you remember who were the authors of the model? Was I mean, I can look up on archive, of course, but yeah, remember.
No, I just remember that it's one of those effective models on color glass condensate, but I think the paper is from people from BNL. So there is Adrian Dumitru and some others, but I'm not sure if it's actually their model or not. It's just a collaboration that is, I think, trying to give consequences that arise from that framework.
That's interesting.
But you can check this one and
yeah, that's probably also for a discussion. I mean, it's an interesting topic to understand, because I mean, it's not definitely not expected in PP, because again, we don't have that low X effect. So I would not have expected at all. I mean, in PA and AA definitely, but not in PP. But yeah, that's good. If there is some model, we're expecting this.
So Christoph, I think there was at some point, at least there was the argument that the number of tracks, the number of particles produced also helps you to scale up the saturation scale. So you have like a modified saturation scale because you have a high number of events. At least there was an argument at some point that was, maybe that's
okay. That's interesting. Yeah.
Yeah, possibly for future talk, I will enter in those details, but I focus on the experimental procedure here. But
yeah, I mean, of course, yeah, no, I mean, of course, no, it's not a reproach by far, just to understand, and it may be good, I mean, also for the workshop that we'll get in 1 year to dig into this. I mean, to ask also maybe to understand what's going on. Yeah, so it's a good point. Yeah, thank you.
Thank you.
Yeah, again, thanks a lot, Javier, and for the nice talk. And maybe we should now go on with the next presentation.
Martin, there is one question from Farid, I guess. I saw a raised hand.
Yeah, okay, please. Yeah.
Just a very quick comment, if I can give my 2 cents here. So yes, I think one perhaps does not expect the color glass condensate to work in PP, but yeah, it's again related to the number of particles produced. So for events for high multiplicity, you could expect that you're probing regions that are dense and have a large saturation scale. So if you think of the proton as hotspots, then when these two of these hotspots collide, they will produce a large number of events, and perhaps it's appropriate to apply the color glass condensate for these events.
Okay, I see some local region of the proton where you have a higher density of gluons. That people were thinking also about this. I remember at the time of ERA, looking for this hotspot inside the protons. Yeah, okay.
Yes, so perhaps this is manifesting, but
yeah, it's very interesting.
Thank you.
Okay, I intend now for another time to go to the next talk. Let's see whether it works this time. But I think it's good. I think it's good we discussed here, and I think I also want to encourage everybody to raise their hand whenever they want to say something. So I'm very happy about that. So next talk will be now by Georgios on top quarks and the Little Bang standard model. So whenever you...
Yeah, can you hear me?
Sure. Yeah, very well.
Let me share my screen. Okay.
Okay, looks great. Thanks.
Thanks. Yeah, so thanks first of all for the kind of invitation. Yeah, I'm going to talk about some experimental studies that we did at LHC, more specifically within the context of CMS collaboration, studying top quarks, not at let's say high pile-up 13 TV, but understanding in a bottom, I would say, putting them within a standard picture of a system that we might create in nucleus, and even in smaller systems, as Javier told, like proton-nucleus and even proton-proton collisions. So let me briefly give an outline for those not so familiar with top quark. So that was one of the last particles we discovered in standard model at Tevatron, and since then we actually performed quite detailed studies now at LHC. However, so far we didn't see them in let's say in nuclear collisions at all, in which there is a conjecture that we create a strongly interacting form of matter, colloquially known as quark gluon plasma. So if you ask yourselves what if top quarks could bring as extra information in that QGP studies, first of all is that at LHC at least, top quarks are produced mainly by gluon fusion. So they are quite sensitive probes of what is happening to gluons inside the bound nucleons, which currently I'm going to show a slide later, our knowledge is quite limited due to the lack of any data constraints. Then in the final state themselves, since top quark has an intrinsic time decay, it can probe the QGP in, let's say, in a time series. I'm going to show a more detailed slide about the main idea behind that. So this is the reason why at LHC we initiated the dedicated study program of at least for now top pairs, since the cross section is higher than, for example, just single top quarks. So in other words, going full path from more elementary or fundamental, within quotes, collision systems like PP to proton-ion, lately even ion-ion collisions. However, for those familiar, LHC simply collides just 1 month maximum per year. So these analyses are really statistics hungry. So I'm going to close with some prospects in runs 3 and 4 and high luminosity LHC. Just one slide.
I gotta get my earphone. So okay.
That's not the question. Okay. How I would simply manifest to me two illustrative examples. What is different, at least what we measure differently in the LED relative to PP. One of them is that this jet quenching. So where we think that while the partons transverse this strongly directed matter, the energy gets redistributed in the surrounding medium. And one of the ways to experimentally manifest that is when we taking the particle yield in lead, and when we scale them to PP, we see these striking modifications as a function all over PT. And also a second class of experimental observers is this, which translates on different mechanisms for hadron production, is some phi correlations, which also depend on PT. So now this is a nice illustration also from CMS, that while Pythia can grasp the hard part of the event, gradually going to lower and lower PT, we start to see something slightly different. What we expected with no, let's say, QGP formation over what data is telling us. But in order to characterize QGP, we have to be sure that we totally, or at least we understand accurately our initial state. And as we were doing in proton-proton collisions, we have dedicated nuclear PDFs in order to describe how nucleons, when they are bounding within nuclei, how they behave. And luckily, there is, as highlighting in this summary table, quite some interest from the theory community to model that initial state. But the main message from that is that while we have not so many data points relative to PP, even the most of them reside the low Q squared. And that's the purpose of colliders like LHC, that we can have really huge jump in kinematic coverage. Here we're highlighting the electroweak bosons, and you can imagine C-stop quark is even more massive than Z and W, who can even probe a bit higher Q squared scales. So a bit words about this final state, why top quark would be interesting in that context. So the jet quenching measurements that manifest as this modification factor as shown before, the majority of them, since they are produced simultaneously with the initial collision, do not have any information of the time scale of the QGP. Contrary to that, the top decay product, the top quark decay products have really a great potential to resolve whether the QGP is, when the QGP is formed and what is their lifetime. And the main idea is that we can use these TT bars as a probe of QGP from, and more specifically, their semi-leptonic decays. So in one leg, we can have this leptonic decay of top quarks, which is really clean experimental-wise. So we can really tag one electron, one lepton, namely one muon, or one electron, and let the other tag, let the other leg, probe the QGP, which is in that case is the QQ bar adena. And in that case, since there is an intrinsic decay time, it has, let's say, a span over different QGP lifetimes. And when we ask ourselves, sure, but how then we are triggered on that, let's say, lifetime onset, we found that this is correlated to top quark PT. So the more energetic the top quark is, let's say, the higher the QGP lifetime we can probe. So if we can study the top quark PT, we can really span a large time scale of the QGP lifetime. Since this statistics hungry, for the moment, that's just an heuristic, so we have pheno studies. I'm going later as a prospect to see what is the lifetime of QGP that we can probe at high luminosity LHC. So let me briefly start. what is the cross-section. So from simply perturbative QCD, from PP, going from PP all the way to lead-lead. Of course, the striking feature here is that since this is a hard process, it scales as with the atomic mass of the involved nuclei. So going from PP to PLED, we get enhancement of A, and going from PLED to PP, we get another factor, so A squared. And relevant just to this simple scaling formula, we even expect a further enhancement, namely to these so-called nuclear modification factors, which for the moment in the kinematic range that we expect top quarks to be decayed, we have a pretty large uncertainty from the theory side. Here we are highlighting one of these two of the state-of-the-art nuclear PDFs, and that's on the other hand, let's say the idea of measuring top quarks with the aim to pin down, hopefully, the current theory uncertainty at that region. Before going to the experimental results, for them that were not familiarized enough with how many data LHC delivered so far, here I'm highlighting a nice comparison. On the left, what we get in PP, in a regular PP run 2. You cannot the scale. We're talking about femtobarns. While on the right, it's the luminosity that we deliver nuclear collisions. Please note the scale. This is picobarn. So we're talking about, as a take-home message, about 2,000 less nuclear data than PP, which is fair because mainly we're not running LHC simply in some months compared to 4 years in PP. But also, as a general reminder, LHC was not meant for that type of collisions, although our accelerator colleagues proven quite ingenious and managed to even deliver proton-ion collisions, which wasn't even meant for. It was not even in the design of LHC. But thanks to it, we started having this nice event displays, which is, from experimental point of view, quite a mess. So we can ask ourselves how we can discriminate top quarks out of this very large background. So this is a real event display from a very central lead collision reconstruct in the CMA detector. So we're a bit lucky, I would say, in top quark, because it's a multifaceted top quark. There's no unique event signature. We have many of it. So depending on how the associated W boson decays, we have a multitude of final states. And for the moment, the cleanest ones, although we sacrifice some statistics, but that's always the case, is the one that involves at least one lepton in the one leg. And the other leg will either to be again a lepton, which we call a dilepton final state, or as I said before, when the other leg is a QQ bar. So we have the lepton platet, so semi-leptonic final state. And then the analysis goes like, we have our detectors are not, say, ideal. We have to define our visible phase space, namely dictated by the kinematic requirements on the physics objects. And then since always top quark is associated with a big quark, so it's their stamp, let's say, we can really take advantage of the BZ multiplicity as nicely, for example, shown here, or jet multiplicity in general, in these lower energy PP collisions, where you can see that the presence of the D-bar is really associated with higher number of jets in the event. But even then, that's not sometimes good enough. We have to refer to rely on state-of-the-art analysis technique. So experiments really rely on a multivariate analysis for understanding, for identifying the bit jets in the event and even extract the signal. Sometimes, because this first ever analysis, we should be careful that we're not mimicking the background as signal. So sometimes we're referring straight from data to extract the background. And lately in CMS, we applied some blind approaches. So we starting with analyzing part of the data set before extracting to the whole data set to avoid any internal bias in our measurements. And at the end, we simply extract cross sections like likelihood fits to not to event counts, but some distributions to enhance our signal to background ratio. So let me briefly start with the similar analysis of the three. So the PP, the low PP energy, which in that case is also a low pileup, contrary to the 13 TeV high pileup. Here it's a nice event display of candidate top quark. And indeed it's striking that how clean these event signatures are in that conditions. Some motivation why we cared at this funny energy, since also the statistics are not so great. As I said, we're talking about picobarns instead of femtobarns. First of all, going from Tevatron to LHC, there was a relatively huge gap. So that it was a nice opportunity to check whether what is happening in between them. And then there's a complementarity between lower and higher energy collisions. So as I said, top quarks are mainly produced by gluons, and in lower, the lower you go in energy, the higher the probe is in X. And it is interesting in that region. So high X gluons that mainly some BSM scenarios manifest themselves. So we can probe better the gluon PDF inside the proton. And then, of course, experimental wise, that was a nice reference for our upcoming nucleus-nucleus collision study. So with that dataset that we had back in 2015, that was the first measurement at a new energy at the Large Hadron Collider at 5 TeV. And we were glad to see, of course, that the measurements within the current uncertainties of about of the order of 10%, nicely agreed with state of the art. So with perturbative QCD and state of the art proton distribution functions. And then when we check the impact on the gluon PTF, indeed, we see that when we include this data set relative to a baseline feed from HERA, we see some increased probing of gluon PTF using this data set. So once we were confident that we can extract top quark in let's say non-standard collision systems, we went ahead and checked whether we can do the same in proton-ion collisions for the first time. Here probably I can skip this slide. So it was just a motivation why we're actually colliding proton-ion at LHC. Javier did, I think, made a very nice intro. Just an interesting statistic, I would say that that paper from CMS is the third most cited in PLB. So there's really a huge and immense scientific interest in that type of collisions. So here, that was our first search of TT bar in nuclear collisions. We looked at the semi-leptonic final state. So when one of the W boson decayed to a QQ bar, and here is the dijet mass, depending on whether we can reconstruct bit jets in the event. So on the very left is when there is no bit jet in the event. You can see that most of the data is nothing more than background. But then when we start requiring the presence of the bit jets, the top quark signal nicely pops up, and mainly when there is 2 bit jets in the event, actually the majority, if not all of our data is commented with the presence of TT bar. And then that was a very nice moment when we then combined this dijet mass with the bjet in the event to see whether we can reconstruct the top mass close to the expected value of 170 order of GeV, and indeed that was the case. So this is the proton ion data compared to what we expected from theory. Very nice consistency check, and that's one of the moments, let's say, that the whole community needed to go from the first peak of TD bar at Tevatron to proton, something that was more non-elementary collision like proton ion, like 20 or so years. So compare that to theory, although still it's even a bit less precise than the reference data set. So order of magnitude of 20% uncertainty. Still, we could see that compared to state-of-the-art theory prediction, we could grasp, we could describe, our theory could describe our data within 1 sigma or so. And compared to exactly to the scaled PP data, we can see that consistency is quite good. And of course, we need more data to discriminate whether there is something happening between PP and proton ion collisions in this very high Q-squared scale. Let me close the experimental part with the first evidence of top quark even in nucleus-nucleus collisions for the first time. So this analysis was, let's say, the expertise was built on the previous one, but given the more challenging experimental environments, you can see that how large the background is. In that case, we went for a dilepton final state, not for the semi-leptonic final state as before. So we sacrificed even more statistics, but we have very striking final state signatures, like here, very clean dilepton final state going out of the background. So we have the electron and the muon in 2 jets reconstructed. So if we did the math, so the perturbative QCD cross-section times the luminosity that CMS recorded in 2018, we expect more or less 100 events. So large, okay, not high statistics, but large enough to go for the first evidence of that final state. Just to say how we defined our physics object, since mainly our background is low PT, we targeted a relative high transformative physics object. So both our electron and electron should be relative high, and within the kinematic acceptance of the CMS detector. And of course, since we don't have to include low mass QCD resonance, our dilepton mass is relatively high too. And once we looked at our data, we saw that all of our dilepton final states are described quite well with from our simulation. And so, for example, here is the dielectron and dimuon, which of course dominated by the Z boson production. But the cross flavor final state, we can see also nice agreement, more dominance of TT bar. And just to say that that's not, although that's not typical in heavy ions, that's one of the first analysis at LHC that we scaled our predictions really to luminosity. And we're very glad to see that we can describe that our current theory can describe the data very well. So that gave us confidence to do a bit more elaborate analysis, as I said in the beginning, some multivariate ones. In that case, we went for some relatively standardized method in our field. It's called boosted decision trees. So instead of cutting by hand at a number of variables, we have our algorithms that correlates properly then and spit out some MVA output, which is shown here for these three final states. So in dielectron, diimmune, and really the cross flavor final state. In the signal dominated region, the data are compatible with the presence of TT bar. So when we translate that to a cross-section measurement, that's close to what we predicted from PQCD, and invert that to the number of events, that's close to the 100 order of magnitude to what we initially expected. And the last part of that analysis is that since so far we didn't look a bit in detail in the presence of pitch jets, that was a second level of analysis selection. So when we start looking at pitch jets, whether our signal is still consistent with the presence of TT bar. In that case, that's a bit more complex than before, because you have to optimize the pitch jet reconstruction, and we found that we can really identified about 70% of the cases properly the pitch jet coming from a top quark. Here is a nice representation of this pitch jet multiplicity in the event. So the three jets with the highest identification score, again the dielectron, in the immune background dominated states, and when we look at the cross flavor final state, TT bar really start to pop up, and mainly in when we start requiring two bit jets in the event, as in the proton ion case, it's really essentially background field measurement. So almost all of our data can be grasped by the presence of TT bar. So we repeated the measurement as before with the BDT, but split in that case in the number of bit jets in each region. And again, in the cross flavor final state, it depended on the presence of bit jets, but mainly when we required heavier and heavier flavor content, TT bar starts to pop up and populate our phase space region. So compare that to our state-of-the-art theory. Indeed, although as before, our precision is still limited by statistics, but we could grasp within 1 sigma or so how well we think PQCD describes these conditions at very high Q squared as compared, for example, to proton-proton case as before. So this closes my experimental part. And as I said at the beginning, simply I would like to highlight some prospects with top quarks and even these heavy enough particles like the electroweak bosons. Just to highlight what is the prospects in runs 3 and 4. So contrary to what we have so far, we expect a kind of 5 times more data than that we currently have in proton ion, and similar jump, if not more, in proton ion case. So it's really we're really enthusiastic about the prospects of the high luminosity LHC. One of that is that we did a projection within CMS. So far, we were measuring TT bar inclusively in that conditions, given the statistics. But we said what will happen, whether we can project that to the higher luminosity that we expect in high luminosity LHC into a bit more differential studies. Here we're highlighting the lepton rapidity from top quark, and we can see it starts probing the uncertainties of the nuclear PDFs. And on the right, for those not familiar, there have been some proposals lately, because there is no, there are some good reasons for colliding lead-lead LHC, but there's nothing unique about them. So we could start thinking of colliding lighter ion species in that case, we're highlighting here like argon, and you can see that within the same running time, we're getting a huge jump of top quark yield in the case that we had collided argon-argon instead of lead-lead, for example. So what we can do with that, with ion-ion and high luminosity LHC, similar to the differential studies in proton-ion, there are theory predictions already published. So we can see that top quarks start probing these nuclear modification regions, and some further constraints, of course, are expected from very similar final states like digits. So that's quite interesting too. And closing with this proposal to extract the QGP lifetime using top quarks. Overall, the reach is quite promising. So at high luminosity LHC, we can, like here down, we can distinguish some low duration scenarios like up to 2 Fermis maybe of 2 Fermis of QGP lifetime. And of course, we can even think for future colliders from LHC, when these ideas could really pay off. So we can really, like an FCC type of collider, we could actually discriminate the whole evolution of the QGP, so up to 10 Fermis, so very large QGP lifetimes. Maybe it's okay just to say that there's also complementarity between top quarks and W bosons. So we can even probe very nicely the lower X region, contrary to top quark that probes the high X regions, that W bosons are mainly agnostic. And just to close, in these prospects of lighter ions, that's the same for the Z boson. So from the baseline scenario of lead-lead, assuming that even the same running time, but with lighter ions, we're getting huge improvements in the event yield. And there was even some, although that's to be taken with some grain of salt, comparing what is this final state modifications between lead-lead and argon-argon, which more or less we found that it's not so drastically different. So this even further, let's say, enhances the argument for converting from lead-lead to lighter ion species like argon, for example. So let me recap. Just to say that at LHC, it's the first time that we have 4 center of mass energies. So all the way from 5 to 13 TeV in a top quark measurement. And for the first time, even 3 independent collision systems. So proton-proton, proton-ion, and ion-ion collisions. So it's Run 2 initiated a new era specifically for that dedicated nuclear modification studies using top quarks. And this quite interestingly concerns both the initial state, so probing the nuclear PDFs at very high Q² values, but also the final state. So how well we think the partons interact with this QGP. And overall, the prospects with these hard probes in high luminosity LHC are quite optimistic, and it's a very crucial program because we would like to extract very precisely the initial state, so how our bound nucleons behave before we create any QGP. And that forefront LHC could really be a game changer. And as I said, there's really immense interest from the community in LHC nuclear data. And interestingly, one of the main advantages of top quark is that we can really access the QGP density evolution, and more specifically, top quarks could be a new tool. So we manifested already at LHC that we can extract experimentally, but mainly at high luminosity LHC and in the prospects of high luminosity LHC and even light ions, that idea could really pay off. And overall, the community for now should really ask itself whether it's time to refine the modeling of the more dilute system and optimize the choice of what could be the optimal species that we can run at some point at LHC. And of course, there is even a community that could take advantage of that light ions for searching BSM complementary to PP. So many thanks, that's it.
Yo, great. Thank you very much for this very nice talk. Please, questions, comments, audience, it's your turn. Let us know in case you some curiosity. Raise your hand or just speak up. It's fine, I think. Okay, seems to be there's no doubt, no comments at the moment. So maybe we can also, in case something comes up, maybe we can also push it then to the discussion session. I think it was a very nice talk, very interesting.
So maybe one. So what can you elaborate a little bit on the? So we have top events in lead and proton lead, but how exactly we can study, for example, the formation of quark gluon plasma, for example? Is it a function of the multiplicity in the events, or how do you do it?
Correct. So ideally, as we're doing, is to form a nuclear modification. So here, as we're doing with other quarks, ideally, although for the moment, okay, I don't think we can probe the PT dependence of top quark, but even just 1 point should be enough. I mean, to scale maybe in rapidity into beams, scale what we're measuring in lead to PP. And in principle, yeah, someone could even do that. So here, sorry, again, going back and forth. Already we have two ratios that we can form, although with, you can imagine, would be high uncertainty. Scale form the ratio proton ion to PP in data. That's one, and the second ratio comes from free, since we have the very same center of mass energy, is ion to PP. But yeah, ideally with with runs 3 and run 4, we'll have, as I said, hopefully 5 to 6 times more data. We can start doing this nuclear modification as a function of kinematic variables. Maybe not so many beams as the Bs or C quarks, but definitely 2 beams could be great. Yeah.
Thank you.
Okay. Also, thanks a lot, Jurgis, for the talk again. I think we should now go to the next talk, because we just tried now on schedule. So the next talk would be by Farid Salazar on gluon imaging using azimuthal correlations in diffractive scattering at the EIC. So whenever you're ready.
Can you hear me?
Yes, I can hear you very well. Thanks.
Okay, great. So And I guess you can see my screen now, right?
Yes, looks.
Okay. So again, thank you very much for this kind invitation to this workshop. I hope I can meet you in person sometime soon, maybe next year. And I would also like to start by saying that I'm very excited about the strong 2020 collaboration that Nestor spoke about before. Among the goals of that collaboration is the study of DMDs and next to leading order computations. So today I will not discuss those. Today I will talk about diffractive scattering, in particular diffractive J-psi production, and what we can learn at the EIC about the gluon distributions in this process. Okay, so this is the outline of my talk. This talk is based on the work that is shown here. And this work was inspired by work by Yoshitaka, Feng, and Bowen. So we looked at their paper and then we figured out we could extend some of those ideas to J-psi. They consider deeply virtual Compton scattering in that paper. And then Heikki, Kaushik, Bjorn, and I pursue this project. So the outline is as follows. I will first talk about diffractive heavy meson electroproduction using the color glass condensate effective field theory. I will take a short detour to discuss DVCS first because it's a bit easier. Then I will discuss azimuthal correlations with the electron plane, and this is something that has not been paid too much attention in recent years, at least within the small X community. Then I will show you some numerical results based on an impact parameter dependent McLaren-Venn-Copeland model. And at the end, if I have some time, I will briefly discuss incoherent diffraction and fluctuations. Okay. So first, let me give you a motivation very briefly of why diffractive measurements. So perhaps I don't need to give a huge introduction because Kong told us about diffractive measurements in a previous session, but let me remind you of some of the basic things. One of the reasons it's interesting is because the transverse momentum acquired by the produced particle, let's say a photon or a dijet system or a J-psi, is conjugate to the impact parameter of the target, of the proton or the nucleus. So if one studies this distribution, which is, for example, shown here, if you want to study the spectra, one can access information about the impact parameter by a Fourier transform. So one can access information about the size of the target, how it looks, the kind of distribution, color charge distribution inside it. And here in this plot, you see HERA data for the production of different vector mesons. And you see that the IPSAT, which is the impact parameter saturation model, describes the data fairly well. And here you can see the extraction of the proton size from this kind of data. So again, one can access information about the size of the proton and the nucleus with these measurements. Another reason it's interesting is its connection with generalized parton distributions. So more precisely, the Fourier transform of generalized parton distribution. So now we can access, again, impact parameter information. It's just the same, these two are, I'm talking about the same thing. This is in contrast to semi-inclusive processes, which are sensitive to transverse momentum distribution functions. And if you want to learn more about those, I invite you to look at Cyril and Piotr's talk on Thursday, but today we'll focus on exclusive processes and impact parameter information inside the proton or nucleus. Okay, but besides this plot that I show you, what else can we learn from diffraction, right? So in the plots that I show you in the previous slide, one has the T dependence, the momentum transfer dependence, and where we can learn information about the impact parameter. But what if we want to learn more? What if we want to learn both about the impact parameter and the momentum of the gluons. So what you can have in mind is, for example, the Wigner distribution, which captures both variables. Or in the language of the CGC, we want to access correlations between the dipole vector and the impact parameter. So there are a few observables that have been proposed. One of the most interesting ones is this exclusive dijet production, which was proposed in this paper. And then it was studied a bit on these two papers. And one can access the Wigner distribution through this process. And while it's interesting, there is a challenge that if one wants to remain in the small x regime, the invariant mass of this dijet system has to be small. Otherwise, you will be sensitive to large X physics. And this, in turn, implies that the PT, the transverse momentum of the jets, is small, which is experimentally challenging to reconstruct. But there is another alternative, and that is to look at DVCS. But so here, one needs to measure two things, right? If we want correlations between the impact parameter and the momentum of the gluon, you better have two things that you're measuring. It's not enough just to measure a J psi or a photon. We need two things. So what can we do? If we have two things, we're gonna have a large invariant mass. So what can we do? Well, let's keep in mind that we have the electron in DIS at our disposal, and we can measure azimuthal correlations with respect to that electron. So that's the idea of this paper. And then, as I said, we extended it to J psi, as I will discuss in a bit. And the advantage is that the invariant masses are not too large, so one is more deep into the small x regime. I should point out this paper, very recent paper. I think it was put on our archive yesterday with another alternative, which is to look at a diffractive pair pion production in UPCs. Now, our approach is we have to go beyond IPSAT, because IPSAT only has information about the impact parameter. But now we want correlations between the impact parameter and the dipole vector. In other words, we want correlations between the momentum of the gluon and the impact parameter. And this is missing in the IPSAT. So what we had in mind is to use a CGC setup with an impact parameter dependent MB model and gene walk evolution. And that's what I will show you in the next slides. Okay, but first, just to have an idea of the processes that we have in mind, let me take a detour and discuss DVCS. Okay, so we have the production of a photon, exclusive production of photon in the final state. And these are the two channels for DVCS. So you have one channel that is initiated by a quark and channels initiated by gluon. And we expect this to be the dominant channel at small x as it is coupling to gluons, and gluons dominate distributions at small x. But there is an important background, which is the Bethe-Heitler process, which is the case in which the photon is emitted by the electron. And if you want to, I will not discuss this any further because the focus of the talk will be J psi production. But if you want to learn more about the interplay between DVCS and Bethe-Heitler process, I suggest you look at this paper. Okay. So how do we do this, right? So how we go about computing this process in the color glass condensate? So as usual, we have this dipole picture. So this picture is very similar to this picture here, but now we resume not only two gluon exchanges, but multiple gluon exchanges. Okay, this is the idea of the CGC. And this is effectively captured in this red rectangle, which is an effective vertex, which is shown here, which is summing all the different interactions. And the approach that we follow is using momentum space rules with covariant perturbation theory approach. This is as opposed to Lycon perturbation theory. Of course, the results are identical, but I think there is some nice features about this approach that are perhaps more familiar with someone who is who is just being introduced to the field. So the way one does this is, just use your standard QFT rules with these effective vertices in the CGC. And if you want to, by the way, if you want to learn more about how this approach, this covariant perturbation theory approach, can be applied not just to LO processes, but to NLO processes, I would like to mention that Paul is going to give a talk on Thursday about NLO computations in this program. But let me get back to this process. Okay, so here we're focusing on the subhadronic amplitude of this process. So we are just forgetting for a moment the lepton part. And so we have an incoming photon, which splits into a quark anti-quark, scatters from the shock wave, and then combines to a photon, which is the DVCS photon. Here we will have the amplitude. We can have transitions between different polarizations. So your incoming photon and your outgoing photon do not necessarily need to have the same polarization, and this is important for this talk. And in the CGC, since in this process you have the scattering of a quark and anti-quark, you're going to have two Wilson lines. Each Wilson line is associated with these effective vertices, and it pretty much encodes the color rotation of these color particles, quark and anti-quark, in the presence of the field of the nucleus. All right. So I apologize for this busy slide, but please follow me here. So this is the results that we obtain. So it's very similar to what you get in Lycon perturbation theory. So let me walk you through some of these expressions. But first, let me say that for a moment, we're going to take the virtuality of the outgoing photon to be non-zero. Okay, so if you want to recover the DVCS case, just let the virtuality of this photon Q prime to be 0, and then you get a real photon, you get DVCS. But for a moment, let us take it to be non-zero. Okay, and what you get are these different results. So here I'm showing you the helicity preserving amplitude. So when you see these plus or minus ones, they refer to the two transverse polarizations of the photon, of the incoming photon. And it's called helicity preserving because the polarization is not changing between these amplitudes. Okay, and you get this result. And so if you are familiar with Lycon perturbation theory, you see, okay, we get these Lycon wave functions that one expects. We get this dipole, right? As I said before, we have two Wilson lines because of the quark and the anti-quark. There is something that appears also, which is this all-forward phase, which I think in the first computations of these kind of processes was ignored. It comes very naturally in the covariant perturbation theory approach. And then for the helicity flip case, something interesting happens. So you have similar structure. You have your dipoles, you have your forward phase, you have Lycon wave functions as well, but you have the addition of this phase. So this phase is occurring because now you have different polarizations in the incoming photon and your produced photon. Okay. And this phase is important because, as you will see in the next slide, is going to allow us to probe azimuthal correlations in this dipole. Okay. So, by the way, if we have checked that our results are consistent with the results in this paper. So we just take the virtuality equal to 0 of the final state photon, and we take the masses equal to 0, and then we recover the results. All right. So as I said, we are after this object here. We are after, so if you expand the dipole in Fourier modes, you will have an isotropic part, you will have an elliptic part, and you will have more things. But we are after this elliptic part, elliptic azimuthal correlation between R and B, which you can think of as related to an azimuthal correlations between the impact parameter and the momentum of the gluon. So it's like a part of the Wigner distribution. So in the case of for the helicity preserving amplitude, because one doesn't have this phase here, one will mostly be sensitive to the isotropic part. So if you do this Fourier transform, you will see that most of the contribution for this one here comes from this guy. But now you look at the helicity flip term, and you have this phase here. It turns out that most of the contribution comes from this elliptic part. Okay, so if one accesses this amplitude, or you have the helicity flip of the polarization, one is probing this elliptic anisotropy of the dipole. Okay, it's a bit more complicated because than just what I just said, because of the presence of this off-forward phase. Okay, but in the J-psi case, this off-forward phase is not going to be too large, as I will try to convince you soon. Okay, so that was the detour to DVCS. So how do we connect to heavy vector meson production? Okay. So we take a very simple approach, which of course can be improved, perhaps more systematically, but this approach is to follow the prescription in this paper. And what they do is they replace the Lycon wave functions of the photon in the final state by Lycon wave functions, phenomenological Lycon wave functions for the vector meson. So in this case, we're going to take J-psi. So it amounts to these replacements. And that's why it was important for us to consider the final state photon to have non-zero virtuality, because we want to have its longitudinal polarization. Otherwise, we won't be able to connect with the longitudinally polarized vector meson. So that's the reason, as an intermediate step, we don't consider it immediately to be real. Okay. And one, of course, needs the masses of the quarks, which we have accounted for. Okay, so in this work. And if you want to see more a different approach to these these Lycon wave functions and how perhaps one can systematically improve this, I invite you to look at Gianni's talk tomorrow, where he will discuss some of these things. Okay, but so why vector meson over DVCS, right? Why is it more useful? So there are a few advantages that I list here. So one of the advantages is that now you have massive quarks, unlike DVCS, where the contribution comes mostly from light quarks. And this reduces contributions from large dipoles in this framework. And large dipoles are dangerous because they are sensitive to non-perturbative physics, for which we don't have much control. Okay, so the masses of the quark, in this case, reduce that those effects. It's like if you look at F2 data, structure functions, if you look at F2 charm, would be much less sensitive to large dipole contributions. It's the same kind of idea. And the other reason is that this J-psi will be less sensitive to this O-forward phase, which was making things a bit more complicated. And why is that? So if you look at the O-forward phase very quickly, you see that if this dipole is small, these are small, which it would be in J-psi compared to DVCS, because again, the masses of the quarks, this becomes almost one. Okay, so one can this kinematic or forward phase will have much less effect than the intrinsic contributions which we are after. So this elliptic anisotropy here. Okay, and another important reason is that there is no Bethe-Heitler contribution, right? I mentioned that in DVCS one also has a contribution where the photon is emitted by the electron, so there is no such thing here, and that's also an advantage. One of the disadvantages is that on the modeling of these vector meson wave functions, right? So, but again, perhaps one can improve that more systematically. Okay, so that's why we were motivated to update some of the ideas in this very nice paper to consider the vector meson production in this paper. Okay, so now how do we measure those helicity flip amplitudes, right? Those are the ones that are sensitive to this elliptic anisotropy in the dipole. So how do we access those experimentally? This is where the electron comes in. I don't want to discuss this slide in too much detail, but the idea is that you can decompose your amplitude for the full process now at the electron hadron level, lepton-hadron decomposition, and then it's useful to insert this kind of completeness relation and rewrite this expression not in a basis like a Minkowski basis, but in the basis of polarization vectors. Okay, and if you do this, it turns out that one can access these helicity flip amplitudes by looking at correlation with respect to the electron plane. Okay, so if you are interested, we can discuss that later, and you can also check the paper. We provided many details there. But maybe let me jump to the formula. So now this is the expression at the level of the electron, proton, or electron nucleus scattering. And you can see that these helicity flip terms will produce cosine 2 phi anisotropy of the produced J psi with respect to the electron plane. And in particular, you can see that this cosine 2 phi modulation would be sensitive to this ratio of helicity flip to helicity preserving terms. Okay? So by studying this anisotropy of the produced J psi, one can access these helicity flip amplitudes, and therefore one can gain information about the azimuthal correlations in the dipole, between the dipole size and the impact parameter. Okay, so one can access this. This approach, I think, has also been applied to dihadron and dijet production in DIS. So these correlations with the electron plane are starting to become more popular in the small x regime. And I think Piotr will discuss some of that on Thursday. Okay, so now let me give you some numerical results. And let me be relatively brief as perhaps I'm starting to run out of time. Okay, so let me use a toy model first to illustrate this. Okay, so let us use the GBW model. So it's a model for the dipole amplitude. And the GBW as it is doesn't have correlations between the impact parameter and the dipole size. Okay, so in the GBW as it is, you don't have this object here. Okay, so if you insert this dipole in our expressions for the amplitude and you compute the cross section, you obtain this result. So it shows you the spectra as a function of the momentum transfer. And here we show you various things, but perhaps the interesting plot to look at is this one here. And here you see that the azimuthal anisotropies with respect to the electron plane are very small. Okay, this is because if there are no correlations in the dipole, you will not have much correlations of the J psi relative to electron plane, as I argued before. And they are non-zero because of the presence of this off-forward phase. Okay. In the absence of that off-forward phase, they will be identically zero. Okay. So now, if we turn on by hand, okay, in this simple model, if we turn on by hand these azimuthal correlations, you can see that you have a large V2 and somewhat significant V1, which increases at large momentum transfer. Okay, but most important, this one here. So this simple example just illustrates the fact that if you have correlations, non-trivial correlations in your dipole, or if there is a non-trivial correlations in the impact parameter of the gluon distribution and the transverse momentum of that gluon, they will manifest as azimuthal correlations, in particular elliptic ones, a V2, in the production of the J psi. Now, that was a simple toy model. Of course, we put those azimuthal correlations by hand, but perhaps one can do better. And what we do is we use an impact parameter dependent Maclaurin-Venugopal model, and we add gene walk evolution. So the initial conditions are a little bit different than the usual MB model. now there is an impact parameter dependence of the saturation scale, and this, models the fact that you have a finite object. So the proton is a finite thing, the nucleus is a finite thing, and there is a finite distribution of the color charges. And that by itself will generate asymmetrical anisotropies in the dipole, okay? Because now you will be probing regions that have different color charges, and that would generate a gradient, which will produce this cosine 2 phi. These parameters are constrained by Hera data, or just as spectra, as you can see here. And the result is that the dipole modulations take this form. So these are an illustration of the dipole modulations. You can see a very nice elliptic anisotropy from the fact that you have color charge gradients. And the way they show up is here. So now, again, this is the spectra, and these are the modulations. So you see, so these two solid lines are the V2s, which I would like to focus on. And you can see sizable contributions. They are smaller than what we put by hand by GBW, but again, in the GBW case, it was just completely arbitrary. Here's a more motivated model for this dipole. And you can see there is a decrease with evolution. So if you see the black curve is when the expomeron is 10 to the minus 2, and here is 10 to the minus 3. And that's because the target, proton or nucleus, is going to grow with evolution. So that's going to smooth the color charge distribution. The gradients are going to be smaller, and therefore these correlations will reduce, as you can see here. Okay, so these are the results for the nucleus collisions. So again, we used a kind of similar model. Now we sample using a Wood-Saxon, the nucleon positions. And you can see these characteristic dips. You have seen them in Kong's talk already. The fact that you have a Wood-Saxon distribution and it's kind of related to its Fourier transform, not exactly. And modulations will also have this behavior. Unfortunately, the modulations are tiny. And you can understand them as being tiny because the nucleus is large. The color charge gradients will be much smaller. So these asymmetrical correlations will also be smaller. Okay, so they are less than 1%. I will not bother showing you this plot, the analogous of this plot for this case, because they will be too small. Okay, how much time do I have? Do I have?
Officially 5 minutes, but I mean, you can also go for 7 or so.
Okay, so I think those 5 minutes will suffice, and perhaps there will be some time for questions. Okay, so let me discuss now incoherent diffraction. So in the previous slides, what I discussed was the exclusive production, so coherent diffraction. But in this incoherent case, one is sensitive to fluctuations. Okay, so perhaps I did not discuss this in too much detail, but one no longer is sensitive just to this object, which is in the coherent case, but is sensitive to this variance in the incoherent case. And that is able to resolve hotspots inside, in some ways, able to resolve these hotspots inside the nucleus or the proton, or in this particular plot is the proton. And they have turned out to be important for the description of incoherent production, J-psi production. So in this plot here, these curves here are the coherent production. These curves are the incoherent production. This one, this lower one, is without hotspots for a smooth color charge distribution, and you can see it fails to describe the data, that is these red dots. But once you include those hotspots, you have a much better description. So the question that we posed, and we very, very briefly explore, and we hope to look at this in more detail in the future, is how do these hotspots affect the correlations that I have been discussing in this talk? Okay, so do they show up in some way? So I will just show you one plot. It's very preliminary work, but okay, so these solid curves here this is just V2. These solid curves are for the case where there are hotspots, you have fluctuations of these color charge distributions, and these dash lines are for the round case where you don't have any fluctuation. And you can see that there is significant differences between the case where you have fluctuations or not. Okay. And we hope that this can provide a tool to access the geometry of these fluctuations. So what shape do they take? Are they lumpy hotspots, or are they like stringy kind of objects? It's not possible to resolve that just by looking at incoherent JSI production. You're able to tell there is some structure, some non-trivial structure, but you're not able to extract too much information about the shape or the distribution, because you need two things, right? If you want a correlation between asymmetrical correlations, you at least need two objects, okay? And just the JSI production is not enough. So perhaps by looking at correlations with the electron plane, one can access this kind of information. The other alternative is, of course, digit production, but I'm not discussing that too much detail here. Okay, so this is the summary of my talk. We have been able to identify an observable that is sensitive to these dipole asymmetrical correlations. In this case, we look at JSI production, and hopefully at the EIC that has a higher luminosity. One is able to study these correlations very differentially in the virtuality, in the momentum transfer, and perhaps we can learn about these correlations, and that will give us some information about the Wigner distribution, and perhaps even about the angular momentum of gluons. And we computed these expected anisotropies using the impact parameter Maclaurin-Venugopoulan model, which are the results that I have shown you. And there are some natural directions for this work. So to extend these results to NLO, and I encourage you to look at Gianni's talk. So some of his results will be valuable for us to extend it to NLO. And there is a very nice alternative approach. So as I said, we use an impact parameter MB model, but recently there has been a lot of work by Adrian, Risto, Heikki, and friends, where this 2-point function is not MB anymore, but is computed perturbatively from Lycon wave functions of the valence quarks. And I think Heikki is going to show you some results of how these asymmetrical anisotropies change in this picture, okay, which I think it's very exciting. And then the other thing that I discussed in the previous slides is able to resolve these different hotspots using these asymmetrical anisotropies. Okay, thank you very much. Let me know if you have any questions.
Yeah, thank you so much for this very nice talk. I mean, it was a very nice overview of research. Comments from the audience, questions, please go ahead. Zoran, please.
Yeah, thanks for this very nice talk. I mean, I had a question on the on the very last part, sort of these azimuthal modulations in the incoherent diffraction, yes. Right? So, I mean, the anisotropies you get here are much larger, actually, right, than you had in the coherent case, right? They're sort of factor 4 or 5 larger or so.
Yes.
Right?
Yes.
So is it? I mean, is it fair? And they're also at higher T, right? So is it fair to say that this comes because now you're looking at the fluctuations, and you have, you know, I mean, the fluctuations, you have a lot of sort of small scale structures in the
yes,
in the place
exactly.
that are also present in the center, and otherwise you only have sort of really R and B correlations if you're at the edge more. Right?
That's exactly right. So in the coherent case, one is more sensitive to the global geometry. So one is sensitive more to the edge of the target. But here, one is able to resolve the smallest structure, the fluctuations, right? So the fluctuations themselves will carry information aside of the global geometry, right? So that's the motivation for us to further this study and look at this, yeah.
But this, at the moment, this is a full numerical study, right? You haven't really You haven't
Yes,
really,
yes.
you don't really have like some more analytic insights into this.
Yes, good question. I think we haven't explored too much this direction, but it would be interesting if one is able to have some analytic formula for the fluctuations. I think I looked at some point at incoherent diffraction, and one has this double dipole correlator. One can have an analytic formula for that, and right in the Gaussian approximation at least, and perhaps one can learn something more analytically. But to be honest, we have not pursued this for too much, but it's something that we have in mind.
Okay. Yeah, thanks.
There's another question by Chung Tan, please.
Yes, it's nice talk, but I do have a question. Could you elaborate a little bit on your last point you said regarding hotspot?
Yes.
But you said, could you explain?
Yes.
We are getting broken, I think.
Yeah, I couldn't. I think the question was about the hotspots, but I couldn't. Yeah, sorry. I don't know if it's from my side, but you broke a bit your connection.
Maybe you can repeat, Shung-hee.
Okay. You remarked on the possibility of regarding to the hotspots, the possibly stringy effect. I would like to know what you mean by stringy effect and what kind of expectation.
Yes. So what I was trying to say is, do the hotspot look like lumps like this, where the color charge is distributed? Like if you think of 3 valence quarks, is like this, or is it something more like this, for example, like the color charge density is like this, or perhaps even, I don't know, something like this, right? So how is the color charge density distributed? Is it distributed like lumps in this case? Is it distributed like strings? Is the color charge connected by some kind of strings? Is it connected this way? Of course, this is just, these are just cartoons, these are just models, but we hope that there is a way which we can distinguish these 3 scenarios or different scenarios by looking at azimuthal correlations with the electron plane. Because I think in this paper, they've tried 2 different kinds of configurations, like something like this and perhaps something like this. Heikki can tell you more about it. And they were able to describe this fairly well, but they were not able to distinguish between these 2 different kinds of configurations. Because if you want to resolve, angular, how these are distributed, you really need an angle, right? You really need to measure it, to measure your produced particle with respect to something else. That's more or less the idea, but it's something that definitely needs further study.
Okay, thank you.
So maybe related to this point also, if there are such hotspots in the proton, for instance, or in heavy ions, so sometimes it should be also colorless objects. So would it change also the kind of diffractive number of events that are predicted, or probably some change at some point when we are reaching this low scale, we would expect maybe more diffractive events due to these colorless objects that might appear in the proton, no? Or...
Yeah, that's a good question. So yeah, certainly the distribution of these hotspots and the color charge is going to change with energy, right? These hotspots are not static objects, they are going to evolve. And I think the gene walk predicts like these hotspots to become more smooth and they grow. So if one looks at the energy dependence of these azimuthal modulations, one can learn about the evolution of these hotspots and how they are, they're arranging and growing.
Yeah, that's why I was thinking also maybe the ratio diffractive to non-diffractive, maybe also some kind of sensitivity to this hotspot, maybe.
Yeah, that's a good point. We looked at ratios of, not in this context, in the context of digits. We looked at the ratio of incoherent diffractive to inclusive. but we didn't look at the hotspots. Perhaps it would be. I can give you the reference later if you want to look at this.
Yeah, thank you very much.
Yeah, thanks a lot for this nice discussion. I mean, maybe we should now go to the next talk. If there's no anything urgent else to be said. So thanks again. Thanks a lot for this very nice talk. I really enjoyed it.
Thank you very much. Thanks for the questions also.
Sure. We can also come back to the whole topic soon. We have still a discussion session at the very end of today's event, so we can come back then. For the moment, let's switch to the talk by Heikki, who will talk about polar charge correlations in the proton and initial conditions for the decay evolution.
Yes, very good. Thanks for this opportunity, and also thanks to Farid. So what I'm showing at the end of my talk will be closely related to what he was just presenting. So I don't need to go into too much detail at that point, but okay, let's start from the beginning. And my task in this talk is to present how we calculate the color charge correlator and eventually the dipole scattering amplitude from light-cone perturbation theory approach. And as a result, we aim for getting something that can be used as an initial condition for the PK evolution. This is the work we did with Adrian Dumitru and Risto Paatelainen not too long ago. So as you probably know, there is a lot of successful small X CGC phenomenology out there in the literature, and the recipe is quite simple. I mean, you take the dipole proton scattering amplitude at some initial moderate X, say 0.01 or so. You don't know that, you parameterize it, you need to include some non-perturbative parameters. But then if you have some parameterization, you can do the perturbative PK evolution down to small x, and then you can determine the free parameters by fitting, say, Hera structure function data. And then after this, you can calculate other observables such as, say, RPA, particle production in PA collision at LHC, which is the example I'm just illustrating here, where you see the CGC calculation nicely describing the nuclear suppression factor that Alice has measured. Okay, so a necessary ingredient in all these phenomenological studies is the dipole scattering amplitude at initial Bjerken X. And as I said, in this work, we want to calculate this dipole amplitude from by performing a light-cone perturbation theory calculation, such that actually our result is also consistent with the high X data of the proton structure, not just the small X data. And then as a result, we get the dipole amplitude, which depends on the dipole size, on the impact parameter, and also on the momentum fraction X, and also on the angle between these two vectors, which is then suitable for initial condition for, say, PK evolution or maybe Jim walk evolution also. Good. So how we do it? So first, I'm just mentioning here kind of a common approach in the field that Farid described in much more detail. So I don't need to go much in that. But a very, very common approach is to take an MV model where you derive using, assuming that you have a large nucleus where you have a large color charge density. And in the MV model, the two color charge correlator is local in coordinate space. In momentum space, it looks like this. So Q1 and Q2 are the transverse momenta of the external gluons that I use to probe the proton structure here. And then Farid also showed you how you can promote the MV model to impact parameter dependent case by basically taking the color charge density to depend on the impact parameter. So what we did, we take a completely different, let's say an opposite approach, and we start from the very dilute region. We take the proton to consist of at lowest order only of 3 valence quarks. So we work at relatively high X or moderate X. And then we measure the color charge correlator again by calculating really, say, diagrams that are presented here. And actually, I mean, to be more precise, I mean, this approach has been already developed in these 2 papers that I list here by Adrian and his collaborators. So this is not the new part of in the work I have been involved. But okay, the idea is that so you take the valence quark structure of the proton and then you probe the color charges by attaching 2 gluons. And then in order to go to the next leading order and also to obtain some information about the X dependence of the color charge correlator, we consider this process of next to leading order. Some diagrams are shown here at the bottom. So NLO means that for the valence quark Fock state, one includes perturbative calculation of 1 gluon emission. And then the X dependence comes as a cutoff for the longitudinal momentum of this emitted gluon here. Okay. So the proton state, to be more precise, is illustrated here. So the leading order state is just 3 valence quarks, and then a couple of diagrams that illustrate what you can have at next to leading order. The leading order state can be written as such, where what is shown here, where the important ingredient is the valence quark wave function psi here. So this universal non-perturbative wave function describes really, you know, basically the probability amplitude that you have certain transverse momenta for the valence quarks and also certain momentum fractions xi. And we have somewhat good idea what this valence quark wave function looks like. You can look at, for example, this Brodsky paper, where some parametrizations for this wave function can be found, and as parametrizations that are constrained really by the high X proton structure, like the proton radius or the magnetic moment. And then, so the next reading order corrections, the gluon emission was recently calculated by Adrian and Risto in this paper. And then with the next reading order proton state, I joined the collaboration and we developed a numerical implementation of the NLO calculation. So this basically if you think about different ways of including a gluon emission to the 3 quark Fock state, and then different ways of attaching 2 external gluons, you have quite a few diagrams that you all need to be numerically evaluated. And that's the work we did in this paper here a couple of months ago. And let's look at the results. And let me first stay in the momentum space. I'll then jump to coordinate space and the dipole amplitude a little bit later. So let me show you the color charge correlator, from which I just factor out some trivial prefactor, and then this T2 is what I'm actually plotting here. Okay, the results are shown here first in 2 different momentum configurations. Let's look at those in more detail soon. In the left-hand side plot, that corresponds to the case where the 2 gluons that I attach to my proton have the same momentum, or moment are parallel to each other. And in the right-hand side case, the moment are perpendicular to each other. And the dotted lines here, they correspond to the leading order result. So I just have the 3 valence quarks for my proton, and then I attach the 2 gluons to it. And then the next leading order curves at different X, they correspond to cases where I include the gluon emission correction to the proton state. And then X is the cutoff for the longitudinal momentum of the gluon. And you know that at leading order, I don't really have any X dependence. The X dependence comes only when I do the NLO. When I go to NLO and I have the gluon whose longitudinal momentum I then have to cut. You see that at large X, say 0.1 or so, the NLO correction is small. But of course, when you allow for smaller and smaller X gluons to be emitted, it's not really surprising that the NLO corrections then become dominant. The bands here are just some variation of some regulator that one has to regulate collinear gluon emission. let's not get too much into that. So one particular feature you see here is that the correlator can be either positive or negative. Let's first look at the case where the correlator is negative. That we obtain in the case where the two gluons had the same momentum. So Q1 and Q2 are the moment of these two gluons here. And now in this case, this is actually probing really a two-body contribution. Because if I try to attach the two gluons to one single quark line, then I basically give a large momentum kick to one of the quarks. But then the valence quark wave function on the right-hand side of the diagram would be highly suppressed because, I mean, of course, the valence quark wave function, it prefers some momentum range for the quarks, and then if I attach two gluons to the same quark and the gluons carry the same momentum, I'm giving a large kick, and then on the other side of the diagram, this valence quark wave function is highly suppressed. So it's preferable to divide the momentum to two different valence quarks. This is the this is the leading order contribution that we call cat-spear contribution, or the two-body contribution in the paper. And actually, you can see from the leading order calculation that this diagram comes with a minus sign. And then because the correlator remains negative at NLO, then the same conclusion holds that in the case of parallel momenta, it's preferable to really eventually couple the different valence quarks or emitted gluon, and really so it's really a two-body, probing the two-body structure of the proton. In contrast, if I have perpendicular momentum, then this kind of a contribution is not that heavily suppressed anymore, because, I mean, of course, if the momenta are not parallel, then the absolute momentum of this quark at the end here is not that large, and then it's not as heavily suppressed as in the previous case. And then it turns out after you really evaluate the diagrams that now this diagram is the dominant one. So this is a one-body contribution because I'm attaching to both gluons to the same quark, and this comes with an overall plus sign. And because the contribution remains positive at NLO, but the correlator, then this conclusion holds that this kind of what we call handbag diagram kind of contribution also dominates at NLO. Then we can look at in mixed space. Let me just be quite brief here, and let's only look at one particular result, this solid black line here. So I take a Fourier transform from momentum space to coordinate space, and this is now the correlator as a function of impact parameter. And we find that the correlator here is negative at small b, close to the center of the proton, and only at large b, it kind of follows the density profile, the shape of the density profile, as would be the case in the impact parameter dependent MB model setup, where this particular quantity would be always positive and just proportional to the shape, the density profile, the shape of the density profile. Then, as I said, I want to get the initial condition for pk, and that I can do by basically taking double Fourier transform to full momentum space to full coordinate space. The result is this conversion equation here, derived by Adrian and collaborators some years ago. And then, I mean, I don't really want to go in too deep into this plot, but this just illustrates that now I can calculate the dipole scattering amplitude as a function of dipole size at different x's and at different impact parameters. So I have everything I need to be used as an initial condition for pk, which will be some future project. I mean, at this point, we haven't really studied we haven't really implemented this yet to the pk evolution. Okay, for the last couple of minutes, I think I have remaining. Let me show some consequences some experimental predictions for experimental quantities. One point is that because we can calculate the impact parameter dependence, it's interesting to look at exclusive vector meson production as a function of momentum transfer squared. The shape side T spectra is shown here. The solid line is calculated using the dipole that we get from the light cone perturbation theory calculation, and for comparison, the IPSat result is shown as a blue dashed line. At small t, we have very similar results as in the IPSat, but when the differences can be found at large t, which corresponds to small impact parameters, and that's not surprising because at small impact parameters, we also have very different correlator, even negative correlator, as I just showed you. And in this reason, we actually don't get a Powell, we don't get an Gaussian, but we get some kind of Powell law for the T spectra. Then, as Farid just showed us, it's interesting to look at how the dipole amplitude depends on the orientation of the dipole size with respect to impact parameter. And in his talk, we saw that in MV model, or impact parameter dependent MV model, V2 is positive, and which means that the dipole prefers to scatter when it's parallel to the impact parameter. But now in our calculation, we actually get an opposite result. So we get a negative V2, and you see that the scattering amplitude has a minimum at when this angle is 0 or pi. This can be more, this difference to MV model can be more clearly seen here when I show this kind of heat map for V2 as a function of R and B. The left-hand side is from our light cone perturbation theory calculation. Right-hand side is from the MV model. You see different sign and a different dependence on RB. So how very much weaker dependence is shown is obtained in the light cone perturbation theory calculation. So then I can do the same analysis that Farid just discussed. I can look at the shape side electron correlations in DIS, and then let's just look at the V2 here, because now we remember basically the quantity. This is now not the V2 of the dipole, but the V2 of the electron shape side azimuthal correlations. This is the MV model result that Farid showed you a couple of minutes ago. And then when I take the light cone perturbation theory dipole, evaluated at this particular x, this is what we get. We get something which is now negative, and also the magnitude of the modulation is somewhat smaller. And so then it will be very interesting in the future to really study in much more detail what are the implications of this light cone perturbation theory dipole to observables like this. And also at this point, this is not coupled to BK evolution. So including the effect of the small x evolution is something that we plan to do in the future. Good, so let me summarize. Starting from proton valence quark Fock state, where one perturbatively calculates one gluon emission, we evaluated the color charge correlator of the proton in both coordinate and momentum spaces. We observed significant deviation from impact parameter dependent MV model results. For example, we found different angular dependence for the dipole amplitude and different correlator close to the center of the proton. And as a result, we obtained the dipole amplitude as a function of dipole size, impact parameter, the angle between the two vectors, and the momentum fraction x that we can in the future use as an initial condition for BK evolution. Thanks for your attention.
Yeah, thank you very much for this very nice talk. I see already a question by Farid, so maybe Farid go directly ahead. And
Hey Heikki, could you please go to slide 9? So here, this is photo production, right?
Yes.
How does this change with non-zero Q square? Of course, it will introduce another scale in the process. So now perhaps this power law is not fully, it will not behave like a power law, but have you looked at least numerically how this changes with virtuality?
Not really. This was just the first rough test of what I get if I run my machinery. I mean, Q squared basically affects the distribution of dipole sizes, I guess, I mean, in principle, what you are saying is true, that then I have a at a scale and it could affect this, but I would expect that if it just gives a little bit more weight on small dipoles, and maybe I would expect that the effect of having a finite Q squared is moderate here, but I haven't really looked into that.
I see. And if I may ask another question quickly.
Sure,
so the way you compute the dipole, it is not by sampling rows, right? It's so I think in your previous slide you show it's more like analytically you relate the row correlator, I guess, to the dipole.
Exactly. So this is not an event by event calculation, but
right.
we have an explicit expression for the row correlator, and then I mean it is what it is. I mean, of course, one could do this. I mean, one potential thing in the future is to sample the color charges from the correlator that we calculate, and that's actually something one has to do if one. I mean, I have been thinking about something like feeding this into Gymwalk, and that would require somehow sampling this event by event.
Right. So in this expression that you show here, I guess you guys have assumed the Gaussian approximation, right? So that you only need the 2-point row correlator.
Right. That's a good. Guess. I mean, it is kind of related to the fact that this is only derived in the dilute region. I mean, this result is not. It's only valid when the interaction is weak, and I think it's maybe higher.
Oh, okay, it's like a weak expansion.
Yes. So higher row to the fourth correlator is actually something that I think becomes important only if you try to relax this assumption.
Oh, I see. Yes. Yeah. Sorry, I didn't see that condition. Thanks, Heikki.
Thanks a lot. There's another question by Yoshitaka. So please.
Yes, I was very surprised by this negative V2 that you find, because I thought there was a general argument that the V2 has to be positive. Well, the solution of BFK, for instance, is V2 is positive, and I thought if you just do the two-gluon exchange, I thought you get positive V2. There was a work by Kopeliovich and company, and so what's the, so is this because of the special proton wave function, or how do I make of it?
That's a very good question. We don't really have a good intuition what is actually happening. I mean, in general, if you have that row is basically just the proportional to density profile, then what you can show, like what Edmond and Amir showed, is that V2 is actually positive. But because our result don't satisfy this relation, then we don't really have any theory somehow guidance, and it's a very good question. We don't really have an explanation for this sign.
Oh, okay.
Sorry, so just one quick comment. It must come somehow from this cat ears diagram, right?
Yes, I mean, of course. I mean, if you have only one body contribution, then you have this. Then this relation is satisfied. So it's somehow related to this two body contribution that come with a minus sign. But that's all I can say.
Okay, and then there's another question by Suduming.
Hey, Heikki, this is Kong. I have a related questions for I think the next slides. I think you have this prediction negative V2 related to Yoshitaka's. I wonder if this can be looked at Hera, right? Are you aware of any experimental data to test it? I mean, this sounds like it's a measurements that can be done
yes.
with what they had before. Of course, they didn't publish this observables, but do you think this could be explored?
So Hera has tried to measure this V2 kind. I mean, they don't call it V2, but they have looked at the electron vector meson or an electron.
Like a row?
And they have it for row and shape psi, I think. For shape psi, the result is consistent with 0, if I recall correctly. We looked into that a little bit, but then we didn't really find anything that useful to compare with.
Okay.
I think it's more like a lack of statistics, as far as I understand, that they were not really able to extract this cosine to phi modulation.
Okay, I see.
For row, they have some results, but then, I mean, for row, the results, I don't, if I now recall correctly, for row, it's more than just consistent with 0. I think it was non-zero, but then for calculating row is more, I mean, the theory uncertainties are more tough.
Okay. Okay,
Yes.
I see. So basically the conclusion is probably they do not have enough statistics to really extract this to be properly compared. Okay.
Yeah,
Thanks.
Kong, I'm sorry if I make comment. I think also, if I recall correctly, a lot of the data was integrated over like some window of Q² and some window of momentum transfer, and some of these features kind of cancel out if you have if you integrate. So if one had a chance to look at it more differentially, I think it might be possible to tell more about this.
I mean, if I just look at the comparison with this MV model, I mean, even you integrate with T, I mean, you should still get a pretty big or positive values, right?
Yeah, the difference between MV model and this light perturbation theory approach, that's striking. Yeah, that was a surprise for us as well.
Yeah, I was asking mainly not to look for the published results, but in principle to read down the analysis, right? I mean, specifically for this diagrams. I mean, replace the photon with the gypsy and then redo this analysis. I wonder if that could be shine more lights or on these observables, of course.
Because there are still some people doing some analysis. I mean, not many people doing H1 and Zeus analysis. So maybe we should definitely contact the spokespeople from H1 and Zeus and ask them if there are some people who would be available to reanalyze this. Because I remember there were, I mean, definitely some results. With the protons usually were selected by rapidity gap selection for most of the cases, or sometime also by tagging the protons. But I mean, to look it with this new high may be possible with the
I mean, I joined H1 in 2018 and just published my analysis. Everything works. Supposed to is a proof of principle that it should work. And also H1, I cannot speak for Zeus, but they're very similar. That H1 has this results that Heikki was always comparing, right? This gypsy photo productions, very nice data. They have some scintillator at the forwards that can tell whether this is dissociated protons or not. I think it's just their published results. They might not have exactly, I don't know, maybe not exactly the same observables, but like, let's say redo the analysis. I think that is totally possible.
Yeah, I agree. I mean, and this would be very interesting. So, yeah.
Thank you. Yeah.
Yeah, thanks a lot for this very nice comment. Shall we maybe go to the next talk and then come back to this in case you have more things to clarify on this topic? I mean, there was a lot of talks on this, and it's very interesting. Maybe we can come back to this in the discussion session. Maybe that because anybody's going to start very soon. So next talk will be by Oahen on the EIC detector. So whenever you're.
Hey, can you see my screen?
Yes. Can you go full screen?
I can try. And actually succeed.
Great.
Great. Thank you very much for giving me the opportunity to talk to you today. I'm going to talk about the ETCH experiment, the EIC comprehensive chromodynamics experiment. And, you know, Kong gave a very, very nice introduction earlier today about how we study diffraction and saturation at the EIC. So my talk will try to complement that talk by being much more technical, by focusing really on where we are and how we are shaping an EIC detector. As some of you might know, the EIC project is kind of running on steroids. and is becoming more relevant than ever, and is more relevant every day. So I wanted to show you where we stand. I chose to do that through the ECHE proposal that is shaping up, because I'm one of the leaders of that one. But the other big proposal, Athena, and the smaller one, Core, are in a similar situation. So seeing one, I think, will give you an insight as to where we stand as a community, and hopefully get you excited about what is coming actually not too far into the future. So starting off, what is ECHE? ECHE is a collection of scientists from about 80 institutions that are working together to design and build a detector to deliver on the EIC science mission. That's the general thing that we are after. And there's some structure to this whole thing. There's a steering committee led by Tanya Horn, John Lejeune, and myself, and then the groups that actually do work, which is our computing and AI team, our detector team, physics benchmark team, diversity and inclusion, etc. So it's quite an elaborated effort, which is what you need when you have so many people working together. And at the end of the day, what we are really after in ECHE is building and designing a low-risk, inexpensive, flexible, and optimized EIC detector that is capable of delivering on the full EIC physics program. So that is really to have a detector that can be ready to go day one of the EIC and deliver on the physics program. Now you might say, okay, what is the EIC physics program? It's not like the machine is already built and we're running, and there's a pack that decided what we're running. That is all true. Right now, for us, the EIC physics program is largely what was defined by the US National Academy of Science Studies. So there was a study that was pivotal, actually, to getting the EIC approved and getting the project going. And that study focused us on the physics, which I will mention in a second. And so we want to do that. And our guiding principles, and I think that's what sets us maybe a bit apart from other collaborations, is that we first and foremost really want to reuse equipment as much as we can. So without jeopardizing the reach and the ability to deliver on the physics case that we will obviously never do, we do want to save and use equipment that is available from very modern detector, or actually not modern detector, but equipment that is still working very well. So for example, we want to use the Babar 1.5 Tesla solenoid that is an acting, functioning magnet that is going to be used for SFINX. So there's lots of there will be lots of recent experience running it. Lots of infrastructure that exists in the halls. I'm not going to go into the details of that because that's very technical, but those things quickly run up to, to the tens and maybe even $100 million. And lots of detectors that are out there. For example, the STAR detector collaboration recently put in a very nice hadronic calorimeter. That will not be used when the EIC is running, but that can, well, not by STAR, but we can reuse it, maybe even upgrade it a little bit to fit an EIC detector. And all of that saving that we'll have by reusing all that existing equipment, first of all, reduces from the risk of managing to build a detector that's ready on time, from the cost of that detector, or even better, saves up on some places and allows us to put in the money on having more kind of modern and fancy detector components in places where it really impacts the performance. And it means that we are really at low risk, both technically and scheduling wise. Now, there are two possible interaction regions for placing a detector at the EIC, and we actually are studying both. There are a lot of technical differences between them that I will not go into to not make this too technical, but one of the biggest differences between them, which really impacts the ability to do diffraction and saturation studies, is the existence of secondary focusing in what's called interaction point 8 at the EIC. The design does include, at the moment, a secondary focusing far down the building. So after the interaction, on the hadron side, there will be a secondary focusing that will allow us, hopefully, we're studying that right now, to tag on a residual nuclear system. So you can really know if, for example, you only knocked out one nucleon out of a lead ion, you can measure the residual nuclear system, detect it, do some particle ID on it, and assure better exclusivity of your reaction. So that would be a big difference. So we're studying what that adds compared to other things. There's lots of other details on the crossing angles, etc., but those will not have a massive impact on the physics program, as a secondary focus will be that we exist in one and not in the other interaction points. We are working to respond to the DOE call for proposal detectors, so we're really moving forward. and we'll respond to what's called Detector 1, the project detector, which means we should be ready for day 1 of commissioning of the accelerator. And with doing that and also studying both IRs, we really do want to share and support the community vision that EIC science mission is best served by 2 detectors. So we, and I hope all of you will help us, really want to push the project to understand that a collider like the EIC would really benefit from 2 detectors, that some places will do similar physics different ways, but in other places will be able to do very different physics because of features such as secondary focusing that one will have and the other will not have. So we're going for detector 1 and routing to eventually having 2 detectors because we think that's the best way to do this type of physics. So what is the physics that we're all after? Well, in the National Academy of Science, really the three of the biggest questions were, how does the mass of the nucleon arise? How does the spin of the nucleon arise? And what we care about for this workshop, also what are the emergent properties of dense systems of gluons? And that really goes about understanding QCD. It's, the theory, we can write down the Lagrangian, but as we heard in all previous talks and the introductions we had in the morning, there's a lot of aspects of QCD, especially in the very low X region, that we just don't understand, and the EIC should be able to help us with that. After the National Academy of Science report came out, there was actually a big community effort that many of us participated in, which was the EIC Yellow report, where the community took down this physics and broke it down into specific reaction channels and did lots of fast Monte Carlo studies to help define what are the performance we need from a detector and the accelerator, of course, in order to realize this physics. So over there, we're thinking about questions like what are the global properties of partons of the pattern structure of hadrons, multidimensional imaging of nucleons and nuclei and mesons, how we can use the nucleus as a lab to test and study QCD, how we can understand hadronization, look for BSM physics, etc. Now, it doesn't matter how you choose to slice the cake. At the end of the day, the overarching questions is really to understand QCD as the fundamental theory that describes the structure of matter in terms of nucleons, the nuclei, and that's basically where most of the visible mass of the universe lies. More specifically, the type of things that we're going to try and do is we're going to try to measure neutral and charge current inclusive DIS. We're going to measure semi-inclusive DIS and then lots of exclusive processes. And that understanding of what it is that we're after in terms of the measurements help us understand what is the physics we'll be able to do. And most importantly, for what I'm talking about here, which is more on the technical side, is what detector we are going to build to do it. So when you think about really what the EIC will be able to deliver on in its science mission is really a huge step forward compared to what we were able to do so far, first and foremost in terms of the kinematical reach. The combination of very high energy, high intensity polarized beams allows us to extend our inclusive phase space to much, much lower X and much higher Q squared than we could before, where really the cross-section starts to, either you need the energy or the cross-section starts to die out and you need the luminosity. It will all be polarized, of course. So when it comes to understanding the spin structure of nuclei, we'll be able to explore completely new territories. And then when we go to more exclusive or semi-inclusive reactions, such as CDIS, DVCS, and similar, we're really just going to explore a whole new phase space. And we're going to do that with extremely high statistics on a variety of nuclei and with detectors that will allow us to reach really the ultimate sensitivities in terms of our systematics. And in context of what we're talking about this week, really will hopefully help us discover and then study and understand the onset of things like gluon saturation. Well, we think this is more or less the scale, and you can see kind of where existing data starts intersecting and why we're only talking about some sort of evidence and initial evidence for that, and hopefully even before the EIC, the LHC will be able to tell us more, but certainly the EIC will be able to study the phase space that is needed to make very conclusive claims about gluon saturation and many, many other aspects. For example, on the spin structure of the nucleons, where we can see kind of all sorts of constraint plots on what we can say today and what we will be able to say with after a few years of running at the EIC. And we're really going to push out our understanding of gluon distributions and, generally speaking, the structure of the nucleon at extremely low X. So to do that, what we need is a good detector. So beams are not enough. We really need a good Hermitian detector that can measure everything. So this is the standard way we like to think about it. We have an electron beam impinging on a nuclear beam, could be a proton, could be a nucleus. So we need a central detector to measure sort of pseudo-relativities around 0. And then we'll have a lepton end cap, a hadron end cap for the higher rapidities. And then, especially for the EIC, it's going to be crucial to also have detectors at the very, very far forward and far backward, depending on who you call forward and backward regions, to really detect either very low Q-square scattered electrons or very far forward emitted spectator nucleon, spectator nuclear systems, mesons that are being produced, and even very forward jets. So when you take that concept and you start breaking it up into an actual detector, this is what was done in the yellow report. You come out with some general block diagram that looks like this. Well, starting from the interaction point, you would first have some nice tracking. Primarily these days, it seems like everybody are converging on silicon tracking. And after you do the tracking, you get the free momentum of the particle. What you really want to do is PID. So you start with the least destructive PID you have, which would be Cherenkov and LGAT silicon time-based time of flight. After that, a bit more destructive, you're going to put electromagnetic calorimeters. And at the end, the most destructive measurement you can do, which is hadronic calorimetry. So that would be, again, a concept for the structure of an EIC detector, just as a block diagram of how you can do it. In the yellow report, we use this type of block diagrams to really understand what performance do we need, what resolutions are required from the tracking, what PID capabilities, electron pion separation, neutral particle detection, etc. What are those performances that are needed in order to really realize the EIC measurement? Not only to say we have coverage there, but to say we have the resolution and the sensitivity to reject background, get the signal, and do a measurement that would really be informative enough to revolutionize our understanding of QCD, because we know that anything less than that would be a failure of the EIC. It really has to revolutionize our understanding of the fundamental structure of matter, or we did not do our jobs and we want to do our job right. So this would be a central detector, and then of course, again, at the far forward and the far backward region, we would have more detectors that I will show you in a second. So taking that concept, what we've worked on in the last few months is really turning that into an actual detector. And this is, for example, how the etch detector looks like right now. And you can see this already, we have 3D models that really allow us to understand how everything fits together, what intersects with what. So it's not engineering drawings to the level of where the screws go in, but it is not very far from that in terms of understanding intersections and support structures and the whole mechanics of the detector. So this is how etcher would look like. We have an electron end cap that will have some large area micro Harwell or GEMS as tracking. We'll have some electron detection with our calorimeters, some lead glass and side glass, hadronic PID through a modular reach and time of flight, and hadronic calorimetry, which we plan to reuse from STAR, or we propose to reuse from STAR. Then going into the central barrel, we're going to have tracking, very advanced map silicon, which will be developed in collaboration with Alice, as far as I know. And so we'll have some barrel region, and then there will be disks to help with the end cap region. After that, we're going to have a time of flight, again with the AC LGADs for low momentum particle ID, then the DIRC for higher momentum particle ID. After that, an electromagnetic calorimeter. We really, again, want to push out current technologies and use things, very new technologies like SciGlass that will allow us really to get amazing electromagnetic calorimetry resolution. And after that, hadronic calorimetry, which we can reuse from SFINX because the whole magnet comes with that already equipped, and it has good enough performance for what we need. And then on the hadron end cap, again, large area micro hours to supplement the silicon tracking. So a bit further out in this region, we're going to put some more tracking points outside of the magnet. And then a dual reach and ACL guards again for the particle ID. And then we're examining different types of calorimetry, standard Shishlik, or longitudinally separated, without hadronic calorimeter, etc. So this is how an EIC detector is going to look like. And really the other proposals, they differ on a lot of details and magnetic field, etc. But the concept is really, really the same, very similar. For us being a 1.5 Tesla magnet, The core that we're focusing on is really seeing that we can indeed reach the required tracking resolution. So a lot of emphasis we put is on this internal barrel region, the barrel and the discs for the silicon for the tracking. That is the core thing that we face improving. So reusing that magnet and support structure that saves somewhere between, we're quantifying it, could be 50 to even $100 million, which is a big thing with everything that we're going to reuse. But of course, it means nothing if we cannot meet the performance requirements to do the physics. Physics is driving things, not cost, of course. So we are focusing a lot on exactly what we have here, getting more tracking information from the ACL GADS for example, putting in another gemmed layer or micro hour layer outside of the dirt to get more tracking points. And indeed, we've set up this quite amazing group. I'm quite puzzled by them and blown away by them, that really are studying the tracking in full G4 simulations and more effective fast Monte Carlos, where they've also, beyond the standard things that everybody do, with putting these things in, running the simulation, running the Kalman filters, moving things around, multiple scattering, support structure, impact, all of those things, they've developed this amazing AI pipeline, this artificial intelligence based pipeline for optimizing the tracker design, which we have never seen before in that implemented in that complexity. They're optimizing something like 14 or 11 to 14 different parameters that are all important. It's not only the tracking, right? It's on the resolution. You want to make sure that you can reconstruct the tracks fast enough, making sure that you don't have too many ghost tracks. What is your tracking efficiency? What are all the geometrical constraints that you have? And under all of that, run a very advanced AI pipeline for optimization, led by Cristiano Fianelli from MIT as part of this new NSF center we have for AI in fundamental symmetries, fundamental physics. And with that, they're getting quite amazing results. So one example I wanted to show you here is on the right here, what you see are the tracker momentum resolutions, simulated, of course, as a function of particle momentum for different rapidity regions. So this is very central, below rapidity, so rapidity of 1 to 2.5, and down here, 2.5 to 3.5. Red is sort of the baseline that we started with from the yellow report, where people optimize things by hand. We have essentially for the barrel, we have two options, either without a gem outside of the dirt or with a gem outside of the dirt. You see the impact. And then in green, you can see what happens when you let the AI optimize things, and you of course check it by yourself. And you see these massive improvements in certain regions, smaller but still significant improvements in others. And you can see here that even easily almost factors of 2 that we can get by optimizing the detector position and layout and complementarity of the different disks, etc., with the AI. And the nice thing is, if you look at these gray lines that you see running through here, these gray lines are essentially what was defined as the absolute best tracking performance you need by the yellow report. So in order to be able to do all the physics, including kind of the edge of phase space stuff, that really push out the detector performance to an extreme, so much more than you need to do the bulk of the EIC physics. And that's covered, or should be covered, by these gray lines. And you can see how we started off either close or sometimes quite far, and that was a massive concern about using a 1.5 Tesla magnet. But you can see where we are right now, and we're especially meeting spec and very close to meeting spec, and that is a delight to see, and that's very novel and comes from this very much a lot of knowledge that was brought in from people from LHCb, etc., into Etche and implementing all of that. And this is something that is actually very much in our workflow, in how we do everything. So the whole detector optimization workflow that we're working on is AI driven, with of course a lot of back of the envelope checks, a lot of passing the smell test to see that what the AI comes up with makes sense, lots of independent verification, nothing black box here. But we are working on this flow where we really want to optimize eventually for not only things like I showed you now, resolutions, but physics. So you run your physics event generators, you run them through your simulation, you do the higher level analysis, you reconstruct events, you look at the reconstruction of your physics quantities, and then you loop back through the AI model to quantify that, optimize your design parameters, run it again, and through that loop, really optimize your detector, not just for this tracking or that, But at the end of the day, for the best performance on the physics, because we know that lots of quantities like X, for example, are not only reconstructed by the tracking or the calorimetry, but it's a mixture of calorimetry, PID plus tracking, where everyone puts in an input, and you can really have some optimization between all those different components of your detector to get eventually the best physics performance. And that is what HA has been doing with a very massive knowledge that we've accumulated around AI optimization, again, led by Cristiano Fanelli and his group that are working on this. So this is one aspect that we're very proud of, and we're very happy to see that we do meet the requirement, the tracking. PID is also, of course, crucial for everything we do, and indeed a nice combination of Cherenkov plus time of flight covers you quite nicely. So you can see some pithier phase space for momentum versus rapidity, and the region that each detector covers, and of course there's the very far forward region. We'll show you in a second what we can do. So again, time of flight plus reach gives you more or less the PID coverage that you need, and of course the calorimeter supplement that to the degree that you need. And then what's really, I think, unique about the EIC, and we're putting a lot of emphasis on, is the far backward and especially the far forward region, where we really want to be able to measure and tag those particles that are going very, very far forward, and basically essentially along the beamline with small deflection. And then we're going to have a B0 spectrometer here of momentum detectors, Raman pots, which will push as close as we can, very, very far down the beamline, and of course a 0-degree calorimeter, which in our case the Japanese are taking the lead on, and is quite a massive undertaking, very, very advanced with layers of silicon, tungsten, etc., to really be able to measure those very far forward going gammas and neutrons. And there's lots of studies coming out on the archive now from the Yellow Report that are continuing and actually being published as their own papers that are showing what we can get from that. So we collaborated with Kong, who led a very nice study on J psi production of the neutron to understand the QCD origin of nuclear forces. With Diane Nguyen, we have just put out, and Ivica, we've just put out a paper on the archive on how we can drastically improve the theoretical and reduce the theoretical uncertainties that come with studying the neutron spin structure from interactions with polarized helium-3, where you do DIS off of that polarized neutron in helium-3, but you tag on the spectator 2 proton system that goes into this far forward region. And by doing that, you are reducing that small contribution, but not negligible, that leads to a large uncertainty from interactions with the protons that have some polarization in helium-3 that you get from inclusive scattering. And you really can focus in only on the neutron, and we've seen almost an order of magnitude improvement in the theoretical systematical uncertainty of the interpretation of the inclusive measurements by doing this far forward tagging at very low X. We've also been able to see that actually the EIC can cover quite high X in these measurements, going all the way up to about 0.7 if you push the resolutions, maybe even 0.9. So all of these studies are very, very interesting, and they're developing this whole new program that we did not do all that much until now of very far forward spectator tagging that we're doing at Jefferson Lab. Lots of work that was done also in Enrique and other places, and will be core for the EIC. So lots of interest in optimizing our far forward region with or without that secondary focusing I told you about. Where really secondary focusing is key. I think people really need to appreciate that that really is something that opens up new channels that you just cannot do without. And that's obviously very interesting. So with all of that detector technology coming in, with realizing how we optimize everything, we are running now full giant force simulations, and basically are studying now the core physics that the EIC will do. So the things that were defined by the National Academy of Science and repeating the Yellow Report studies, but again with full giant simulations as opposed to fast Monte Carlos. So addressing aspects of nucleon spin, confined motion of protons, 3D imaging, nucleon mass, high gluon densities in nuclei, making sure that we do have the phase space coverage and the resolution to make sure that we can discover saturation, and mapping out quarks and gluon distributions inside the nucleus. And then, of course, we want to do some studies that show unique strengths of HL, like ion tagging, pion and kaon structure that are crucial to understanding the origin of mass. Tanya Horn is leading a very active research group on that. These tagging experiments I just told you about for spin structure, we're very excited about them. Want to see that we can really do it. How I in X we can push. How would that complement JLab? Similar X, but much higher Q square. Lots of things we can learn from that. Nuclear modification in medium evolution, hadronization, etc. All of that is being studied with real giant force simulations, which as an experimentalist, to me, everything I've talked about, is sort of out there in the air until I see these type of plots, which is why I really get excited, where you see that the full simulation machinery is there with the tracking, with the clustering. It's all there, building on a lot of infrastructure that was already developed and optimized for the SFINX detector. There's no connection between SFINX and HX, except for the fact that we can use a lot of the infrastructure that they have built and modify it for HS. So we have full tracking algorithms and again, clustering, etc. I think that except for full particle flow jet studies, more or less everything else is done with full giant force simulation. So this is very exciting for us. And another thing that I'm personally very much excited about, and I think should be of interest to all of you as well, is the international engagement. So just on ECHE, we're about 1/3 international, 2/3 US based, and we've been keeping that balance as we grew from about 30 institutions that we started to almost 80 that we're in today. And there's lots of interest around the world in many, many aspects around the tracking and helping out with the silicon technology through the calorimetry and this around, again, the lead, the SciGlass. Lots of countries are involved in this consortia that we have. Dual readout calorimeters, for example, are state-of-the-art technology that would be amazing to implement at the EIC, and we should be able to implement the EIC on the relevant time scale, and there's lots of leadership there by Korea in collaboration with Japan and others. Particle ID, GSI have lots of expertise with DIRT technologies for Panda, and we're collaborating with them as well. And again, the far forward and far backward is actually all led, almost entirely led by foreign institutions, which we're very proud of. The French have lots of interest in Roman pots, and lots of experience with that. My colleagues from Israel are very interested in off momentum and luminosity monitors. Japan wants to take full responsibility of the ZDC, or we hope that they will do it. And there's lots of leadership on the low Q-score tagger in the UK, especially in Glasgow. And lots of other things that have to do with the general scope of the project that everybody needs: DAQ, triggering, electronics, this AI that we have implemented, again with CNU also, MIT, CNU, Barnell, and other institutions. And you can see there's basically integrated international engagement all over the place. And that is nowhere to, does not mean to say that we are done. By all means, there's lots of room for more collaborators, for more institutions to join and start making contributions from institutional knowledge that they have, and they can weigh in on discussions in the working groups through maybe summer students and summer projects on building the simulation, analyzing simulated data, and helping us really understand what technologies are best and how to implement them. So some of our highlights, we're now running large full-scale simulations. So we've built all the infrastructure, debugged it, and are now doing that. And we're kind of already starting to draft the proposal. DOE wants the proposal is at the end of the year, so December 1st. So this is very compressed timeline, but the groups are amazing, so we get it done. So within a month, we're going to analyze all the simulation data and show the physics extraction, and again, move from understanding delta P over P or P pi separation to actual physics observables, which is the deliverable. And then we're going to do some iteration off of that, write it all up in a proposal that will have lots of supplementary documents, submit, and start iterating with DOE and its review committee on the review of all of this. And really at the end of that, be ready to start hopefully doing the last touches on the design, making really more engineering designs, and start building it. So in terms of where the EIC project is, again, for those that might be a bit less informed, I really am telling you this thing is running on steroids. We have completed CD1 essentially. We're in the middle of 21. By the end of next year, we want to do CD2. After that, CD3. So that's where we're going to basically complete the R&D and design phase. So very quickly, we're going to move from that into a production and manufacturing state, some pre-op, some commissioning, pre-op, and at basically 10 years from today, with CD4A, we want to be able to have a detector to help commission the machine and then do physics, and 2 years after that, hopefully reach maximal luminosity and continue with the full physics program. So this is actually quite fast, and I am personally very much excited about it because the community seems to be pushing very fast and making these deadlines. We were quite worried about making the yellow report deadline, which was also a year-long effort because of COVID, and the community just pushed through COVID in an amazing way. So we're very optimistic. So to conclude, I told you about ECHE. There's again other consortia, namely Athena and Core, that are similar. Athena a bit larger, Core much smaller, but still all of them are working in a similar way to design and build an EIC project detector, in our case based around the Babar solenoid. By reducing this cost and risk, we plan to be ready for EIC physics by CD4A 10 years from now, and as soon as basically the machine becomes operational. The physics program spans the entirety of, that is what's outlined in the yellow report and the National Academy of Science study, and the detector design process is full underway, and there's lots of room to get engaged and contribute. And why contribute to ECHE? Well, because we are a low risk, inexpensive, flexible, optimized EIC detector. In our humble and very biased opinion, we are the most realistic detector to be ready for CD4A, and we're more than happy to collaborate with anyone that is interested in helping us put forward the best detector proposal that we can to make sure we really squeeze all of the physics that we can out of the EIC. And with that, I will conclude and show you some nice animation. Thank you.
Yeah, thank you very much for this very nice overview of the project and the idea of the detector. I like it a lot. So I was watching your animation, which is was very nice. But even meanwhile, already somebody has a question or wants to comment on something, and please go ahead or raise your hand or simply pick up.
I know that we have a discussion following up, so it's fine to move directly.
Yeah, maybe also the talk was, I mean, in this sense, very complete because you presented the whole project. So I don't know, Christoph, there's a question or comment by Daniel, please.
Yeah, thanks for the talk. I'm just curious about the AI that you mentioned to optimize your detector. What sort of AI is it? Is it more than gradient descent? Is it like? Yeah,
yes. It's, I forgot the exact term. It's this Padreva-Front propagation. So it's much more than gradient descent. You cannot do traditional gradient descent on a 14-dimensional parameter phase space where each step costs as much as it costs to run here. So the group is doing something different. The place you can find the reference for that that's been published is Cristiano's work on the dual reach optimization. So you can write to me, I can forward you his papers on this. But they did publish a lot of what they did on the dual reach optimization. That was a simpler project, very complex still, very impressive, but simpler than what we're trying to do here, or they're succeeding to do here. I'm not an AI person myself, I have to admit, so I cannot give you all the details. But one thing I didn't say about ECHE, we are completely open, and not only completely open for people to join, but whoever wants to log into an ECHE meeting can just log into an ECHE meeting. So we have a calendar online, and you can come to our AI meetings and see what's being done, talk to them, challenge them. We're always happy to do that, even with people who are not formal members of ECHE. This is a community effort, so anyone is open.
Cool, thank you.
Yeah, maybe I have a question related to the Raman pot detectors. So the, or two questions. I mean, concerning the Raman pot technology, did you discuss, I mean, with the people from Totem, for instance, that developed all the technology to run all these Raman pots at a very high luminosity and so on. And it took, in fact, many years of developments with CERN. And then concerning the detectors, do you plan also to have some timing, fast timing detectors inside the Raman pot or not? Or
Yeah, so right now what they're talking about for the Roman pots is actually using ACL guts for them. And that will give you also very fast.
Yeah, indeed. Yeah. Okay, very good. Thank you.
Okay, then I think thank you again for your very nice talk. So thanks a lot for this presentation.
Thank you.
And we come to our discussion session. Yeah, I mean to the discussion in general, which is planned now. So time-wise, we're already at the end of the discussion session. So, but I think in case somebody, if the Europeans are still awake,
It's not being late for Europeans, but I mean, you can discuss any topics that we had today or new ideas, whatever people may think of. I mean, either something that we discussed already partly or something else. I mean, depending on people. There were quite already many discussions during the talk, which was very good. But, probably we'll stop here and we reconvene, I think, tomorrow. I mean, if people agree, tomorrow.